yeah, so Paul Odiwo Agola, he went home back to Homa Bay after his PDC, and he realized all his friends wanted to know what he'd been learning. Well, he went to Uganda. He'd never been out of the country before, so it was all very exciting. Big deal, really. And after a few days of sort of pondering, he didn't really know how he was going to explain what he'd learned to his friends, his community. So he started his own training center. Within a couple of weeks of doing his PDC, he started teaching courses, and he set up a training center called Permo Africa. And he's now reached and trained literally hundreds and hundreds of people. He's changing the DNA, if you like, of his region. It's incredible. It's grown. He's done lots of outreach. In 2017, he came back with some of the more people from his community. I trained them. He did the same in 2018. He came back again with more people. And then later on in 2018, he worked with us in the refugee settlements. So we've really had a chance to work together, and I went and visited him. I've been to his place. I'll find the photos of that if you're interested. But just talking to Paul this morning, and he's just trying to build a GoFundMe campaign. It's it's ambitious. It's quite a lot of money he wants, but he wants to create, where they live, they don't have water. They're close to the Lake Victoria, but it's very arid there, and it gets hot, and there's no running water. He wants to sink a borehole which will give access for water to 48 villages. Can you imagine that? I mean, firstly, I can't really imagine not having water. At the moment, because they're in drought, they're running around with buckets of water trying to save their plants. But imagine a scheme that could give water to 48 villages in which we have trained lots of different people in permaculture. It's a sort of a game-changing scale of things. And just to think what a humble, small sort of start that all of this has had. So I don't know, I'm going to try and interview him later and see if I can get a little bit of video and get it out there, because he's going to have to reach thousands and thousands of people for this to be successful. But somehow it struck me as an interesting possible campaign to get behind. But anyway, it's been such an interesting journey to work with, well, people all over the world, actually, mainly in UK, but we've always had people, international students on our courses. And then since starting working in Africa, it's kind of exploded, really. It's very, very interesting. And so in working with us, working with Sector 39, I hope you feel that you're slowly, even though you're just sat at home, being drawn into a network. And I hope, feel, especially if you're a social media person, do communicate and chat with other people in our network. And anyway, enough of that now. But I just thought I'd share that with you. It's interesting. It's interesting to think about, because I think it's all about collaboration. It's all about cooperation. I think to face the problems of the world and the challenges that we face, we're going to have to join up in all sorts of different ways and find common cause, find a sort of common purpose. And we live in fairly desperate times. So we can change the world by changing ourselves. Change starts from at home, starts from the self, from the home, from the community. But also somehow it relates, it connects globally. And I'd like to just touch on that. So this document I've just been using as a jumping off point was a summary of key points that we put together for some of our trainees, so that they could have it on their phone, perhaps if they were doing training in the bush or remotely, wherever. But it's designed for everyone, really. And obviously we've been looking at it. And today's principle, well, let's look at, I want to actually look at 2 or 3 principles today to kind of sort of bring more of these ideas to the fore. And we started looking at some examples of permaculture designed systems yesterday as well. So here we go. Permaculture principle number 2. Then remember, it has a sequence. We start with the acceptance of change. Then we observe and interact. Now it's catch and store energy. Those pictures that I showed you last night of the rainforest in Trinidad and Tobago, just green everywhere, leaves on every surface. And what's it trying to do? Catch and store energy. That solar energy is the only energy that's coming into the system, only new energy. Make hay while sun shines. Okay, that reminds us that catching and storing energy is strategic. It's time-based. You know, you have to be there on the right day. You know, right now there's so many blackberries. Blackberries. You go out and you pick buckets of blackberries and elderberries, loads of them. And it's almost like, oh, I'll do it tomorrow. So many busy, so many blackberries. And then one day, bang, they're gone. You've missed it. It's timing as well. Catching and storing energy involves timing, strategy, a bit of planning, anticipation, because we know really when certain seasons are coming. The icon is the sun in a bottle. Apparently it's a milk bottle. I never knew that. It's an Australian milk bottle. But and that represents a store of energy. You know, jam, honey, anything is a store of solar energy that's been captured. And obviously it gets us through the times of winter and the times when there's less abundance is by capturing when there is abundance. And just another little thing to note, just to remind ourselves, is that sometimes when something is abundant, we don't value it. It's very easy to take something for granted that seems to be everywhere, but then suddenly when it's not there, we then really, you know, we miss it. So we mustn't become complacent. Some of the things that we take for granted now that are hyper abundant might not be in the future. It might just be at a period of time when it's very easy to buy, I don't know what, computer gizmos or whatever might be of a time. So it's also remembering, it's good to remember that too. Inappropriate concepts of wealth have led us to ignore opportunities to capture local flows of both renewable and non-renewable forms of energy. That's really true. There's a lot of hydro potential in Llanrydder and Mochnant, but we don't bother because electricity is cheap. We have a sense of wealth which is inappropriate because we're so invested in fossil fuels. We we think the cheap food and easy transport that we have now is something that we can take for granted, and maybe it isn't. On when we look at energy a bit more deeply, I do a bit of an analysis on transport, and I think that transport is one of the things that we're most exposed on, that we have that we can't take for granted. Okay, have a lovely day, Lydia. We see you've got to dash. Yeah, we are recording, and it'll be there for you later. So I hope you're managing to catch up, and have a great day. Okay. Identifying and acting on these opportunities can provide the energy with which we can rebuild capital, as well as provide income for our immediate needs. So look, if we can catch and store energy, it doesn't just allow us to survive, it might allow us to invest in capital, more tools, more equipment, the things that allow us to actually to raise production into the future. We might feel that we're living in austere and difficult times. Maybe we're not. Maybe we're living a time of absolute abundance that perhaps we might not see again for a couple of generations. Think about that, because the economic systems that we're relying on are very shaky, and so lots of things that are currently cheap, tools, or I don't know, information. I'm a big downloader of information. I also keep my books because I don't necessarily assume that the internet's always going to be there, or it might be dysfunctional, or it might be censored. We don't know. Some of the sources of energy include sun, wind, runoff water flows. There's many wasted resources from agricultural, industrial, and commercial activities too. People who live in cities or on urban fringes are very, very good at recycling, very, very good at spotting the value in sort of discarded, products of industrialism. And again, we can't assume that those things will always be there. Everybody's interested in building out a straw bale for straw bale houses, or building things out of pallets, or I don't know what, things like that. These are byproducts of industrial processes, right? Straw bales is to do with big monoculture kind of agriculture. Things like wood chip and pallets are a byproduct again of maybe mismanagement of forestry and things like that. So for sure, if they're around, use them, but value them. Catch and store that energy. Understand it might not be there forever. You know, we developed and devised very efficient cookers and wood pyrolysis gasification cookers made out of old paint cans and tin cans and buckets and things like that. Great. We managed to replicate that in the southern part of Uganda. But when we went to the northern areas, to the refugee settlements, there's nothing like that in the waste stream. No one's throwing metal away at all. So we had to then go back to the drawing board and build things out of clay. So I'm going back to what's on the handout. Something I think I've added in. I think I've got the memory. Nature's annual surplus of twigs, grasses, and leaves, which can easily be converted into compost and humus. Yes, I've seen those. Sean was commenting about earth chips. I've got a couple of photos I'll bring in of one. Again, a wonderful use of reclaimed and recycled materials. And yeah, using recycled tires, which are actually toxic, horrible things. There's millions of them lying around. And, building with these things is one way of almost getting rid of that waste. The earth chip house is also kind of earthquake proof because they've got that the rubber within it can absorb some of that shock. So yeah, valuing these resources and seeing what they are and realizing that actually they might be a one-time harvest. We might not be continuing to produce these things. I think one of the most undervalued forms of energy and undervalued resource of all is twigs. I'm a big fan of twigs. Narrow diameter wood that's grown this year, that can be harvested and dried very easily, transported very easily, combusted very easily to create a lot of heat. And also things like grasses and leaves and things could be composted to create humus. In the UK, we have miles and miles of hedges, and they used to be managed as a resource to create poles for coppice, for making fences and animal shelters and all sorts of things, handles for tools, many things. But now we just flail them with a big tractor and just smash the ends off to make them smaller. But they lose their functionality as hedges because they're no longer laid, so they're no longer stock proof. But also is all of those flailings, those little bits that are being chopped off and chipped off hedges, sprayed up the bank is what they do. They just leave it on the ground. That very quickly breaks down again and returns as carbon dioxide to the atmosphere. I think there's a massively wasted resource there, and we'll explore that later. So the most important stockpiles of future value, this is David's Holmgren's thoughts, may well be fertile soils with high humus content. Here's another way that I look at it is, imagine if our economy collapses or if our currency is massively devalued, what are the things that will still hold value in that world? And fertile soil is still fertile soil. That is definitely a really good thing to invest in. Perennial vegetable systems, that's a really good thing to invest in. It's definitely going to keep its value. Trees and food forests and tree systems, again, a very good way of protecting value regardless of what might happen. Bodies of water, tanks, stored water, passive solar buildings. I also think, though, the make hay while sun shines, catch and store energy. Another really important element of this is, yeah, thanks, Michelle, exactly what I was going to say. It's brilliant. Knowledge, information, and also social connections and community, the sort of intangible things that have enormous potential value. Specifically, Michelle said not just knowledge, but seed saving. And actually, kind of think we need to set up a seed saving project even within our own sort of groups, because that is such an important thing. And you know, it's the area that the corporates are really going for. They want to control the genome of our food plants, or you know, they can see great market opportunity and great market power by being able to do that. Some countries, they are forcing farmers to actually making it illegal to save seed, which is an absurdity. But through the power of some of these global trade agreements and corporate power, they, countries like Tanzania have been forced to sign agreements to say they will arrest farmers who save seed. Crazy, terrifying. Anyway, saving seed is a skill, and we can also naturalize seeds to be, you know, more appropriate to bioregions. If you save seed from your garden in Newtown year after year, and you take seed from the strongest, healthiest plants, you'll start to create varieties, if they're open pollinated, that are actually adapted for Newtown. This is what we used to do, and that's another way of bringing diversity back into it, back into production. I'm interested in wheat. I'm just developing a new interest in wheat, and I've posted something on the Academy blog about that, I think last week. Heritage wheat strains and how we might be able to recapture some of those. So yeah, anyway, there we go. So last night I introduced the subject of soil, and I'm going to go really more deeply into soil and water this morning, because of the energies that we need to store. If you like, that's the building block from which we can build everything else, is fertile soil and stores of water. So we're going to focus on that for now. Okay, you should be able to see that: soil, water, and landscape. Catch and store energy. Okay, let's start by thinking about soil a little bit and its structure. Oh, great! Sean was saying he watched Dirt, and yeah, it's a really good film. I posted on the yesterday's page. Really good, and hearing voices of people like Vandana Shiva and Wageri Matai, is it the Kenya lady? Yeah, really fantastic, and getting that empathy and real interest in soil is key. Let's go underground. We'll start from the surface. What we're familiar with seeing, here's a tree stump or tree. We can see its roots, little bunny rabbit. We've got some plants, some grasses. So the surface of the soil is covered generally in living plants. That's what we're used to seeing in those living plants. And of course, and the debris of those living plants is around them. Bits of sticks and old flower heads and seed heads and, you know, dry grasses and things like that. And so we've got a lovely mix of living plants and plant debris on the surface. So the living plants are really maintaining the soil. If you remember that they're channeling energy down to their roots and feeding the microbes. And that we're going to have most of our aerobic life, the really active, complex life forms, the aerobic life forms, are going to be in that top few centimeters of soil. In fact, there's more, again, we got a little flavor of that, didn't we, with Jeff Lawton's introduction yesterday. But there's more complexity of life in that soil than anywhere else in the planet, in that topsoil. A good scoop, handful, bucketful of topsoil, there's more organisms in that than there is people on Earth. There's probably in a handful there's more than people on Earth. In a bucketful there's more organisms than our cells in your body. I mean, it's awesome. The complexity of it is exciting to think about. And so these communities of microbes, you know, are being fed all the time. There's like little trickles of sugars of and also of the leachates of the breakdown of the things of the, you know, the dead matter being broken down on the surface. Imagine also, you know, the worms and the sort of various different life cycles happening in the surface, that it's constantly mixing the soil up, aerating it, lots and lots of nutrient exchange going on. And it's very, very, very important surface layer that we've called here in this diagram. It's called the A horizon. Sometimes it gets called the O horizon. I'm not quite sure the difference, but it's black and crumbly. It's high in organic matter. It's teeming with soil life. Also includes the life that we can see, you know, insects and worms, grubs, bacteria, algae, fungi. All of those things are breaking down organic matter into humus. And this is the main area of root activity. This is the main area where plants are feeding. These top 15 centimeters of soil, really, this absolutely teeming with life. As we go a little bit deeper, and again, so we can see most of the roots, most of the activities, most of the exchange is happening in that surface. As we go down deeper, they can see, you know, trees and things do have deeper roots that anchor them into the ground and access water. A lot of the actual feeding is going on at the surface. As we go down into the soil, it gets lighter, and that's because there's less humus, there's less organic matter. It's maybe have a coarser texture. We might see larger stones and rock particles. And you can imagine that this B horizon is being constantly enriched by what's trickling down, filtering down from above. And there's a really interesting exchange going on between the A and B horizon. And then as we get a bit deeper, we get into the sort of weathered, fractured bedrock, a weathering bedrock, it says here. We can imagine we're getting closer to the actual, you know, the ground rock itself. Now, there's different kinds of, yes?
See box folder.
Sorry, Michelle, can you just say that again?
I can't see any picture. There's only the Dropbox folder. You're talking about a picture on the screen, and I don't have it.
Oh, okay, right, got it. Okay, thanks for saying that.
My connection keeps dropping out, so I'm not sure if it's something that's happening from my end or from...
Can you see that now?
Yeah.
Okay,
yeah.
Okay, thanks for pointing that out. Sorry, that was yeah, okay, yeah. So it's a bit confusing navigating between all these files, so sorry about that. Yeah, okay, so this is what we were talking about, this A horizon, this rich, dark, air-filled, filled of life. This is the action zone. This is where a lot of it's going on. I was just bringing you down into the B horizon, where there's still a lot of very important stuff going on, but it becomes more anaerobic. There's much less air down here. So the kind of things that are happening are slower over longer periods of time. Worms will come down here if it's cold or dry to protect themselves. And in fact, there's many different species of worms. There are some that live only in the composty bit at the top. There's some that live in the A horizon soil, and the others that come really deep down. So that's good to know as well, to think about as well. I'm going to say something else, though, which is an interesting thought. Is now we all know that when the moon is full, its gravitational pull is slightly stronger, and the amount, the water in the oceans is kind of like pulled towards it, stretches, doesn't it? It becomes slightly elliptical, and then this creates the tidal effect, the sea going up and down. Well, there's been some research and thinking about the impact of the moon on soil, and in some ways, because there's all this stuff about planting by the moon and what have you, and in some ways it sounds a bit witchy, a bit, you know, a bit sort of speculative and a bit sort of magical, but maybe there's some truth in that and some reality in that. If we just think about this, And I'm all this just intrigues me to think about how the world works. But as we go down into the soil, yes, the biodynamic people are really into that sort of moon planting thing. And thanks, Sean. And some of the people I work with swear by it, but they don't necessarily claim it works. So what they do is they claim that it makes them pay attention. And if it's a good seed sowing day, then why not sow some seeds? It's something which, if you like, keeps you focused on the garden. So whether exactly, it's hard to measure these things, but it's still good, if you like, to have a system because it makes you pay attention. So imagine as we were to travel down through this soil, it's moist, but we get to a point now where it becomes wet, it becomes saturated. So maybe down here there's water just sitting on this bedrock and in these cracks that's kind of there, not permanently, but long term, shall we say. And to a certain extent, water will also be, under the action of gravity, will sort of trickle downhill as well. So imagine the pull of the moon. Imagine that gravitational effect that has on the soil water, on the reservoir of water in the soil, and that the effect of the moon can actually cause the surface of the soil water to rise too. So imagine the surface water rising slightly, and then as the moon falls, it goes down again. So all of these pores, and I already said this top zone of the soil is aerobic. It's got oxygen in it. As those microorganisms respire, as they're burning energy and giving off carbon dioxide, the air in that soil is going to get a little bit stale. So you can just imagine that as the moon waxes and wanes and the soil reservoir rises and falls, it pushes out air. It sucks air back in. Soil's actually in some way breathing, but there's a line somewhere between aerobic at the top and anaerobic below, and that line goes up and down. So that's another mobile, dynamic edge. And somehow just on that edge between the aerobic and anaerobic frontier, there can be all sorts of important exchanges happening. So something very, very interesting going on within the soil, between the aerobic and the anaerobic kind of frontiers. And think about how that might interact with all the soil life and the microbes, and how important it is that the sun can breathe, that the soil can breathe. So we're going to think a little bit further on now about how important it is to not compact soil, how to keep it open so that it can allow not just for there to be air spaces within it, but for the air to flow in and out and to circulate between the life in the soil. There's a gaseous exchange happening all the time. So this is all very, very important. Okay, I hope you're not struggling, Michelle. I keep seeing you flickering on and off, so good luck with that. Okay, let's look at this on a slightly bigger scale, a slightly different diagram, but kind of saying the same thing. So there's also to think of, again, there's a carbon and oxygen cycle going on around within the soil, that the trees are pulling in CO2 and pushing out O2. And at the same time, the soils, there's respiration within the soil, giving off carbon dioxide. And as the soil frontier goes up and down, there's oxygen penetrating deeply into the soil and energizing the microbes within that. So as trees grow, as plants grow, as they live and die, we can imagine how they've got long roots going deep down into the soil, anchor roots, tap roots. And in some ways, as the tree lives and dies, so does its roots. So that's also leaving organic matter, carbon-based residues deep in the soil. So there's a process over time that the carbon that was in the air through plants is translocating, it's moving, it's shifting deeper and deeper into the soil over time. And the deeper it gets, the longer term stable it becomes. And to resolve out the climate crisis and many other issues, people simplistically say plant trees. Well, okay, plant trees are a store of carbon, but they're very short-term store of carbon. As we've just seen with all these forest fires and deforestation and you know, drought or something like that, all that carbon is very quickly released again. It only becomes stable once it's in the soil, and the deeper down into the soil it gets, the more stable it becomes. So it's talking about soil aggregation. We get a little bit deeper down, we get much more long-term stability. So again, is surface plowing, just opening up the surface, this top little sort of O horizon, that has a certain kind of impact on the soil. Doing sort of proper turning over the soil, when you maybe turn over the whole right down to the A horizon, that has another kind of impact for the soil. But in doing deep plowing, which is what's happening more and more, bigger machines, we're having a bigger impact on the soil, it's disturbing it in a much more profound and deep way. So we're in the minimum tillage game. Minimum min-till, they say, farmers say, min-till, minimum tillage. We don't want to disturb these top layers any more than we can. By using mulches and doing other strategies and techniques, there are ways of doing zero ploughing, zero digging gardens. Sometimes we might want to do some ploughing or digging, but we do that very consciously. Think about the seasons, think about the rain, think about, you know, the damage that we might be causing, and we try and keep it very shallow. In Africa, we did some remediation of land with ploughing, and we had a bullock. We had 2 bullocks and a little hand plough. And what you realize is that when you work with those tools is you can't cause very much damage to the environment with a bullock plough, because it's only just turning over the surface. It's not like a big 700 horsepower John Deere tractor, you know, maybe really almost mining the soils, really. Okay, so getting a feel now for what's going on down there. Yes, when you go to Trevlack, comment from Sean, but Ian, in the 10 years since we've been working at Trevlack Farm, they've moved away from, very low tillage. They're now entering minimum tillage territory, and they're learning how to do it without ploughing. You're going to see some of that and see some examples of how they've managed to do that over time. Okay. So, of course, if we go to different climate zones around the world, we see different types of soil. And we're just going to look at 3 classic types of soil here, and understand a little bit the differences. I'm also going to go to, okay, these are soil types by climate zone. So in the temperate zone where we are, we would expect to see a really good accumulation of soil, of humus, rich surface soil in this surface zone or O horizon. And our A horizon, a bit underneath that, again, the subsoil is again really quite high in carbon, full of nutrients, and have a certain amount of life and oxygen in it. So in the temperate zones, we have deep, rich soils. And we can say that if we were to look at this, if we're looking at these layers of the sort of surface layers of the soil, and including the organic matter, the life on the soil, at any one time, if we took a snapshot of this temperate soil, we could say 2/3 of the available nutrients in the system at any one time are in the soil, and about 1/3 is in the canopy. So farming in our temperate climate works quite well. You remove the trees, and you've only lost 1/3 of the nutrients, and now you've got all of the soil to farm, and you can plow it up and turn it over and mix it together, and you can farm that for years, decades, before you start to run out of soil and reach these sort of mineral pans further down, where the minerals get leached out by rainfall. So we have very forgiving, very tough, long-term healthy soils in the temperate zones. Some people look at tropical zones and say, oh, it's so easy, everything grows so fast there, you can just grow everything, it's, you know, it's easy for you. That's not really true. I think that here in places like Britain, Western Europe, we have some of the most benign growing conditions on the planet. Okay, we have winter, but we don't have plagues of locusts, we don't have fierce droughts, we don't have that really strong, potentially destructive sun. And say we have these deep, very, very forgiving soils. Now, I think there's a statistic, there was an article somewhere that I saved, but saying we've only got, I don't know, 20 or 30 seasons left before we've mined out our soils, even in Britain. So again, because it's an abundant resource, soil everywhere, lots of it, and it's deep and it's strong and it's fertile, we've taken it for granted, and we treat it really, really badly. What's very visible to me here in our little part of Wales is quite a few of the farmers have switched to doing biomass crops, and specifically growing maize. And they don't harvest it until about November. So just at the time when it's starting to rain a lot, there's a lot of, you know, and we're going into winter, so there's not much life in the soil. They come with their huge tractors, they mow all the maize, they mince it all up into mush, send it off to some biogas plant or something. And then they leave the soil bare all winter, November, December, January, February. The soil's bare. The roads are just thick with soil. I mean, you can just see it all just washing out. It's the opportunity cost of growing that maize for a biofuel is the loss of your topsoil. That's not worth doing. That's not a good trade. So we take our soils very much for granted here in the West, and it's because they are so good. They are so amazing. Jump to the tropics, and you have a different setup actually. In sort of humid tropic systems, you have a lot of biomass, more biomass, more layers of biomass. The biomass can be more closely together because the sun's overhead, so you've got a more constant solar import coming in. So maybe 1/3 of the nutrients are in the canopy in temperate zones, but maybe in the tropical zones it's 2/3. Maybe it's so, and therefore there's only 1/3 of the available resources in the soils. So our farming systems, our Western farming systems, don't work very well in the tropics. We've imposed our systems that we've used for hundreds of years on tropical systems, and in a few decades we've completely destroyed the soils. Huge parts of Kenya, very, very fertile ground, can't grow anything there now, and we're having to go back and revisit our sort of permaculture techniques and everything to restore those soils. It's all can be fixed, but not easily. It's easier not to cause the problems. So what happens is, as well as that, so there's a lot of leachate. We get very, very high rainfalls in tropics, which washes out certain minerals, which creates kind of mineral pans lower down, which are very hard for plants to get through. So when we're working in the tropics, we work really, really hard to not disturb this rich humus layer, because it's thin and it's fragile. It's breaking down really fast because of the heat and the humidity. The bacterial microbial life is much faster. So everything's cycling. It's like everything's happening on fast forward, whereas things happen nice and slowly here in the temperate. We can stay control of our systems. You wouldn't believe how fast the weeds come, or if you get a problem in the tropics, how quickly something can break down, because everything's like on fast forward. So you can have tremendous successes very quickly, but you can also have tremendous failures very quickly. And I'm not going to spend a lot about desert environments. I don't really have any experience of trying to grow in desert environments. But from reading around, what's interesting is all the nutrients are here. They're all blowing around in the wind because there's very little plant activity. So there's very little nutrients held actually in the biomass. And there's also very little fertility in the soils. Again, because there's not much life, they're too dry and they get too hot. But as soon as we start to put the right things in the right place in arid systems, even in deserts, the life comes back very readily. So we can work with all of these types of systems. Permaculture can work very well in all of these different kinds of systems, but we need to understand the underlying patterns. We need to understand the key differences between these systems. Now, of course, there's lots of different types of temperate soil and different types of tropical soil. These are big generalizations, but I'm trying to give you an empathy for the bigger picture. To say patterns to detail always is our journey. Okay, good, great. So there's our little introduction to types of soil. What words do we use to describe our soils? Do we have adjectives or names or whatever? What things are we used to using to describe our own soils? Often if you pick up soil and you rub it between your hands, you get a sense of its texture. We saw Jeff Lawton going into a sugarcane field, and he couldn't even get the soil, to pick it up. It's all kind of compacted and stuck together. It's been kind of smashed apart by industrial processes. But if you can take that good soil and rub it between your hands, and you can feel the texture, what you're actually feeling, sort of grainy part of the soil, obviously, is the mineral particles within it. If you've got a very coarse soil, you can feel, stones and maybe a scratchy sort of nature to it, and you're feeling the mineral particles. Some soil is like clods, isn't it? Like stuck together really hard, you can't break it apart. And obviously those ones have a lot of clay in them, and clay is very sticky, and it makes a tough, heavy, harder soil. So we could just think about those kind of types a little bit, and then I want to go into also thinking about, well, what's soil actually made of? What's its ingredients? What's if we were to have to write a recipe for it? Well, what goes in the recipe? So the first thing is, soil's made out of rock particles. We know that part of the recipe of soil is pieces of mineral particles, and that those mineral particles have different sizes, and we name them after the size. Sand particles, relatively to the others, are very large. So sand, silt, and clay. There often are certain kinds of minerals that give us the sand, silts, and clays, but at this stage and in this way we're looking at is the size of it. And so a sandy soil is predominantly large rock particles as its basic mineral structure, and a clay soil is predominantly very small mineral particles. So as you can imagine, it's going to create a different kind of soil. Silt sits between the two. We see that there's a real order of magnitude difference between the clay and the sand. So it's going to give us a very significantly different kind of soil. I think that's a good point to make as an introduction. So this table is out of Bill Mollison's designer's manual, and he gives values to these things. A fine clay particle is less than 0.002 millimeters. It's tiny. That's 2/1000 of a millimeter. less than. Typically, clay particles come in at around 0.002 of a millimeter, and the silts come in at order of magnitude. You know, cut a 0 off, and you've got your silt. Yes, sorry, yes, I lost my place there. Sand, again, another order of magnitude. We've got fine sand and coarse sand. So the coarse sand is big. That's up to 2 mil. That's big. And gravels then start to become, you know, bigger and bigger. Cobbles, stones, and boulders. Okay, so we've actually these terms have values. It's just interesting to know that. But that's a better way to remember it. Clay is really, really small. Sand, relatively to it, is really quite big. So it's going to give us different types of soils, isn't it? It's going to have different characteristics. Also, these things can mix together. I'm sure you've all seen this diagram. It's in every book on soils. Is that if it's 100% clay particles, that's the mineral part of the soil, then you've got a clay soil. I mean, that's how we describe it. 100% clay soil has set characteristics, which we'll explore. 100% sand soil, again, would be very large particles. So you can imagine 100% sandy soil would be very free draining. As I said, from the roof garden, I discovered that most plants really like free draining soil. So sandy soil has advantages, but also is a free draining soil. It's going to dry out quickly, isn't it? So it has disadvantages. Silt. And the other extreme is we might have 100% silt particles, and so we've got maybe quite a uniform silty soil. Now, if you go to the Fens, Lincolnshire, those kind of places, you see silt soils, and that's because they've been deposited by rivers over really long periods of time. And mainly where I saw this was in the on the edge of the Wash, and Norfolk, Lincolnshire. So they've reclaimed land there. So big rivers deposited maybe after the glacial period, particles that are all the same size, and then when they've reclaimed, they push the sea back and claim the land. They've created incredibly fertile soils. So some of the best soils in Britain are silt soils in that part of the world. But obviously, it's very rare to get 100% pure of everything. And especially, remember, we're looking at a landscape which has been devastated by glaciation, and then the glacial melt, and then rivers. So a lot of these rock particles and things have all moved around. And so they've mixed up. So you might get a mixture of. So some of the other word that we use to describe soils, we've got clay, sand, and silt. The other word we use is loam, and loam is obviously, it's this lovely mix in the middle. It's this area in the middle where we've got mixes of sand, silt, and clay together, and it seems that that's the most desirable to have. It's like, again, we've got a little bit of the advantages and disadvantages of all three types of particle size, and we might have a really nice loam, or a slightly clay loam, or a silty loam, or a sandy loam, a sandy clay loam. You can imagine now, see how these different proportions might define, help us measure and describe soils. Really, all we're describing is the mineral part of the soil, this bit of it. But that's a good basis for understanding. Okay, so these are USDA classification of soil types by particle size. Okay, let's not overlabel that point. Did you ever do this at junior school? I think we did. We did the jam jar test. You can do it a bit more scientifically than perhaps you did it if you did do it at junior school. But you take a jam jar, any kind of jam or confection, could even be a mayonnaise jar. But seriously, we take a clean, clear jar, and we're going to put 1/3 of it to be filled with soil from our garden, or the soil that we want to test and learn about. Where are we going to test that soil from? We're going to take it from here. we're going to take it from just below the O horizon, just below the bit that's got all the life in it, a bit between the, you know, about here at this depth, just a few centimeters below the surface. So we get an accurate, you know, representative sample. And we fill the water. We've got a third in the bottom of water, 2/3 full of with water, a little bit there at the top, and shake it up. Shake it up a lot, turn it upside down, get all of the soil particles moving, suspended in the air, in the water, get it all, you know, like one of those snowstorm things that they sell at souvenir shops, and then set it down and you can watch it. And gravity is going to take over, isn't it? We've got all of our soil particles suspended in water. So very quickly, if you've got any gravel, if you've got any stones, if you've got any coarse, really coarse sand or particles, that's going to precipitate out at the bottom of the jar very quickly. Slowly, the larger, heavier particles will sediment out. And maybe just within a few minutes, all of your sand particles will deposit at the bottom. And slowly, so will come the silt particles. Now I mentioned a little bit, when I showed you those pictures up in the High Atlas in Morocco, and I said how they were playing with the stream, with the river, to separate out the coarse gravels and the sands and the silts. And essentially, they're interacting with it in the same way as the jam jar effect, is that things will settle out because each particle size has slightly different properties. So if we can create certain eddies in the river or certain traps, sometimes they use little barriers of some kind, woven barriers, then you can actually select which particle size the river's going to deposit. So clever, but it's still observing, you know, it's an observation. We can get an instinct for the makeup of our soil, and we can make comparisons with other ones if we do the test in the same way every time. So it's very important to be methodical about how we do this. If you do it in one part of your land and another part of your land, or to compare it with somewhere else, to make sure you've done the test in the same way. The clay particles can stay suspended in the water, sometimes for days. It might stay muddy. And if you've got your jam jar test has a few particles in the bottom, but it's just like a muddy sort of mess, and it stays like that for quite a long time, then you've got a clay soil. And there's other ways of turning a clay soil, is that you can, again, squish it in your hand. If it's a high clay content soil, you try to roll it into a sausage, and then bend that sausage around into a circle without it breaking. Because obviously we know clay becomes malleable. Those little tiny particles stick together, because there's very little air spaces between them. So when that's moist, they stick together and it creates like a vacuum. So we can get, we ought to, and often if there's organic matter, especially dead organic matter, just little bits of sticks and stuff, that stuff will float on the top, or look, some will float on the top of the water, some will sit on top of the clay, but it's good to do this a few times. So it says here, interestingly, jam jar method of assessing crude soil composition. It's useful for classification. The uses for mud, brick, or pisé work as well, useful for things like that. So if we've got a very high clay content in our soil, we can make bricks out of it. We can construct out of it. So we can find out how waterproof it is if we compress it. These are important things. So soil sample is shaken in water and allowed to stand until layers form. 1 to 20 days. Wow, that's a big difference, isn't it? 1 to 20 days. So if you've got a very high clay soil, it's still going to be muddy many days into the test. Whereas if it's got a lot of particulates and larger parts in it, they're going to settle out really quickly. So interesting. Okay, we can get an empathy for the type of soil we have by understanding the size of the particles in it. Okay, so let's explore the characteristics of those types of soil. So if we've got a sandy soil, clay, silt, or loam, hopefully we're now happy with those terms. A sandy soil is very open and gritty. It's easy to work with, so you feel it in your hands, you can feel those particles. It's sort of scratchy. It's easy to work with. You can get your spade into it because it's not all compacted, and it has good aeration. It's poor at holding water, and it's poor at holding nutrients. So a lot of our nutrients might be quite mobile, mineral salts washed down deep, or nitrates flushed out. So sandy soils can be low in fertility. They need constant feeding with organic matter and protection with mulches or green manures between crops or when fallow. Often they can have a high pH, but leaches rapidly. Check pH every 2 years. What's pH is, what's it, potential hydrogen, I think it stands for. But obviously the pH scale runs from 0 to 14, or 1 to 14, gives us acidity or alkalinity. 7 is neutral. Most plants, most of our vegetables like to grow in a 6, ever so slightly acid, ever so leaning, ever so slightly acid. Potatoes, 5 or even 4. They can do even a little bit more acidic. Most of our plants want to be about 6. The brassicas like a slightly alkaline soil, maybe an 8. So again, just quite close to neutral. If we work with our soils and keep them aerated, keep them mulched and fed with compost, they will tend to be about a 7. And so we can actually remediate, we can fix almost any soil by keeping it covered and feeding it compost. It's what's really interesting is for any type of soil, we need using the same strategy, and it gets us where we want to go. So let's contrast sand and clay because they're very different. A clay soil, it's sticky when wet. We know that's hard to break up when dry. It can set like stone. We might use grit, well-rotted manure, sand, anything like that to help break it up a bit. If we can mix it up a bit. A huge vehicle going past through the village. So here's the interesting thing. Clay soils hold a lot of nutrient. Clay soils are really desirable in terms of their fertility. But obviously they get to be waterlogged, they can be heavy, and they can dry out to be rock hard. It can be very difficult to dig, so it can be challenging to work with. I did a PDC a few years ago down in Herefordshire, a place called Cannon Court. It's an intentional community down there. And the original Cannon Court building is mentioned in the Doomsday Book, they told me, and they had a book about that, which I was looking at. And the Normans, when they settled Britain, they were looking for the valuable areas. They were very interested in finding the clay soils. So although they were challenging to work with, they represented a store of fertility. And so, you know, we know Herefordshire is very famous for fruit growing and things like that. And as I understand it, that tradition goes right back 2,000 years. And those Hereford clay soils were sought out by the Normans. So some soils can be very challenging. I've seen people with very heavy clay. I think they call it a podzol. It's a glacial deposit type soil where rock particles have been smashed to be so small it almost becomes really, really sticky, heavy stuff. But still, if you can get enough organic matter in there, we can work enough, we can improve them and we can make them work for us. So silt has a generally good structure, but it can become waterlogged when wet or very dusty when dry. It's improved by regular additions of organic matter and well-rotted manure. Keep well mulched in summer and when being left fallow. Usually has a neutral to acid pH. Check every few years. And of course, the fourth type, the loam, which is the mixed up of everything else, has great structure, easily worked with, and easily worked into a fine tilth, to that, you know, the fine crumb structure that we can plant into. It's easily maintained with regular applications of organic matter, drains well, but is not susceptible to drought, as it retains water and nutrients well, and usually is a neutral pH. So look, the high draining sandy soil, ever so slightly acid. The clay, alkaline, the clay a little bit acid, and silt close to neutral, and loam close to neutral. So again, these are patterns, not details. We're just getting an empathy for it. Okay, so there's our basic soil types, and they really quite relate to the particle size. We've thought about how we can understand that a little bit and explore it, and we've looked at how that sort of is expressed on a graph. Okay, this is about crumb structure, and this is something which, and when you garden, you observe this. I might go and get some soil, actually. I want to show, let's play with some soil. Give me 1 second. Okay, I've got some soil here to explore. It's out of the raised bed just in front of my house. So it's got a lot of mulch on the surface. The first thing to get empathy and a feel for soil is smell it. And there's a certain smell which we can all we all recognize that smell, and it's the smell of soil. And it's good to be reminded of that. Actually, what you're smelling is the bacteria. That's the sort of the breakdown products of the bacteria that are in the soil. And it's soil that's got a good humus content, that's got lots of organic matter in it, and is nice and moist. It's going to have that smell, because that's the smell of organic breakdown of the bacteria in the soil doing their thing. Now, I don't know how well we can see that. But look how the soil is in little crumbs. It's the particles that it's made out of become aggregated together. I can just sort of crumble that up. Look at it. It's like the topping of a crumble. And I'm getting a lot of that lovely smell. And so I'm getting a bit carried away now. So you can imagine, through the action of earthworms, through the action of all sorts of microbes, so those nutrients within the soil, all that organic matter, is being broken down by bacteria. It's being broken down by mycelium. Along comes an earthworm, and earthworms allow the soil to pass through their digestive tract, and they digest. They eat those bacteria. They're literally digesting those nutrients. And when the soil passes through their body, it gets aggregated together. It's like there's kind of microbial and fungal byproducts that help stick those little soil particles together into crumbs. And what we're always looking for in our soil is a good crumb structure. And even if we've got a very dense, heavy clay, when we work organic matter in it, we get the worms, we get the microbes all moving around, the soil gets aggregated together, gets stuck into these balls or little crumbs. And that creates really lovely little microbial environments, but also then creates the air spaces within the soil that we want for life to be successful. So when you're looking at your garden, especially that lovely dark soil around your house or the well-cultivated areas, you'll notice that crumb structure. Now, the other thing that perhaps you might notice is with soil, see how this is with this one, is if you squidge it together, really squish it, and you can feel the moisture in it. You can feel how much it wants to stick together or not. And again, I'm squishing it against my hand, and you can see in some ways it leaves a mark. It leaves that sort of brown squidgy mark on my hand. That's the humus. The humus within the soil is not, it's not this stuff. It's not the dry grasses and things. This is not humus yet. This is dead organic matter. It's got a long way to go before it becomes this sort of black jelly-like stuff. Humus is like a jelly. It's an emulsion, and it's suspended in the soil, and it's there as a long-term store of nutrient and carbon and stuff within the soil. That's what we want. Yeah, anyway, I forgot what I was going to say now. But so we can see this, that sort of stickiness, that dirtiness in the soil that's the humus. That's what we want. Oh yes, I was going to say is that humus is not water soluble. It's a suspension. It's an emulsion. It's there in the soil, and the plants access it when they need it, or they can team up with microbes, if you like, to access it. So here's a difference: is in industrial farming, they use water-soluble nitrates. So you're putting nutrients on the soil that are water-soluble. So there's two things that are going to happen. One is, if it rains, they'll be washed through and end up in rivers. And secondly is, as the plants respire and water channels through their bodies, as they transpire, they're taking up nutrients whether they want them or not. They're almost being forced to take up those nitrates dissolved in the soil water, whether they choose to or not. And what that happens means that the plants become more distended, they get thinner cells, they're more stretched, and they become more prone to disease. It weakens them because they're distorted slightly. So there's another kind of thought about the difference between organic and non-organic approaches to growing. It's this humus, this stuff in the soil that is there, the reserve for the plants, it's there for them to take when they need it. They're not kind of being forced to take it because it's dissolved into the soil water. So there's a difference too. Okay, so then there's the thing now that it's very hard to think about soil without thinking about water, because you can't really have one without the other. We can't have, the soil isn't going to be useful to us. So the ability of a soil to absorb moisture, to hold it, is absolutely key. And it's an exploration of soil. And look, this is a sand particle. This is a sand particle. These could be silt particles. These are clay particles. So look how we've got a nice mix of different things together. And when we have a nice mix of particle sizes, we've got some lovely air spaces within the soil. These micropores. They're like little caves or cavities. It's these spaces, these edges, these spaces within the soil, that's where the magic happens. It's not specifically this sand fragment or this silt fragment, or this clay fragment. It's the spaces between them where there's air, there's water, and there's microbes. So there's a community. These little micropores, these little cavities in the soil are perfect homes for yeasts and bacteria, perfect homes for amoebas and protozoas, which is where all of those interactions. Remember, Jeff Lawton said, it's not the soil, it's the life in the soil. We have to team up with the life in the soil, is what Jeff said. So let's, how do we do that? Well, the first thing that we do to team up with the life in the soil is we understand these guys need air and they need water. So don't stand on the soil, don't compact it, try not to plow it, try not to dig it, keep those things to a minimum. Can we keep it covered with mulch? Can we feed it compost, 2 inches of compost a year? Can we feed that to the surface of the soil? And the microbes, the worms, the organisms will bring them down, channel them into the soil, bring them, translocate those nutrients further down. You'll notice that this soil has a reservoir of water within it, but that it's not saturated. So this is a moist soil, because although there's water, there's lots of space for air too, and we need both of these things. As soon as there's so much water that the air is pushed out, then it's a bog. Then most plants are not adapted to grow in that environment. They can't grow in an anaerobic environment. They need the association. So you get very specialist plants in wetlands, in bogs, and where there's no air in the soil. They have to have other strategies to survive, and we'll look at that on a future lesson. So in developing an empathy for the soil, we're understanding that in some ways it's these spaces, these micropores, these little caves, these within the soil. That's the secret. That's what we're trying to create. And these aggregated, crummy soils have loads of air within them. And where there's air, there's more activity. Where there's more activity, those worms and things open up channels in the soil, and it gets better and better. So again, what's the upper limit to fertility in soil? Who knows? So next thing to notice, next observation is roots. Plants have roots. Those roots have hairs on them, root hairs, which are very fine and very delicate. And rather than, just think again about the edge effect. Think about this multiplication of surface area. So here's my root going down. It has quite a lot of surface area, but when I put hairs on it, it multiplies that surface area by a factor of 100 or 1,000. I don't know how much, but significant, a lot. Officially, what they call a lot. So yeah, okay. Here we go. So surface area. These roots of plants, it's wrong to think of it sort of smashing its way through the soil, that it's somehow punching its way into the soil. Because if you've got coarse, sharp soil matrix, spiky bits of sand, whatever, that's going to scratch and damage the root hairs of the plant. Very, very fragile. And if they're scratched or damaged, then that's a root in for disease. That's a root in for problems. So more, I want you to imagine that these root hairs probe into the spaces as they find them, and they can expand and open them up a little bit. But it's more like it's threading itself through the available spaces. And in the process of doing that, threading itself through, creating lots of connection, lots of surface area, lots of it's anchoring the plant, and it's also building relationships now where it can exchange nutrients with the microbes that we know are populating this micropore. So there's our relationship between the soil particles, the soil, air and water, and the roots of the tree, of the plant. Okay, so here's a slide. Here's a microscope of exactly this same thing. We're looking at the same little environment. We're looking at the same sort of, this is an actual photo. This is obviously an artist's impression. This is a real one. Here's the root of the plant. There it is. You can see that in section. And we can see on the root there's the hair, there's the root hairs. Here is a mycorrhizal hyphae. That's those little tubes of fungi, and that mycorrhizal hyphae is, look, it's growing into the root hair. It's growing into the plant itself. And as that hyphae penetrates the plant digests it, takes those nutrients away and uses them. In return, sugars are flowing into that mycorrhizal hyphae, into that mycorrhizal fungi, and then that can grow, use the energy for it to grow in other direction. So there's a very important exchange happening on a kind of molecular level there. Here we have a actinomycete hyphae. This is another kind of fungi in the soil, and its spores, and it's digesting, decomposing cells. So here we got, so this one is a saprophyte. This one is a root feeder, mycorrhizal hyphae. It's getting its energy from the roots. This one, the actinomycete hyphae. This one is a saprophyte. It's eating dead and decaying matter. So here it is decomposing some old plant cells. And the digestate from that is interesting to an amoeba. And there's that amoeba feeding on that. And there's a little arthropod, a little beetle or something, eating the amoeba. So think about things are within the soil being eaten again and again and again. There's a whole kind of food chain going on within there. And this is how then the nutrients become transported around by the fungi and by the microbes and exchanged with the plant. Here's a parasitic worm or a nematode. It looks like it's eating these little amoebas, whatever they are. So here's another thing. The other thing that we're seeing is the soil crumb effect. Is this matter here is a clay organic mixture of clay and organic matter in a complex. It's the breakdown of fungi. It's what's, if you like, sticks that soil crumb together. It's the gooey stuff. We've got more nematodes, little microscopic worms, and on it goes, on it goes. So we think about, there's this wonderful, what we can't quite see in this picture, we can see in this is this complex interactions between all of these different organisms, and how there's a very delicate, very intimate relationship between them and the roots of the plant itself. That's how soil works. Okay. Okay, oh, yeah, next one, just taking the time. Okay, so 20 past 10, okay. We'll do a couple more slides and then we'll have our 15-minute break. I've already mentioned this book. I think I've mentioned this book, Lady Eve Balfour, The Living Soil. Lady Eve Balfour was so famous, they've named a potato after her. You can grow Lady Eve Balfour potatoes. I think that's about as exciting, about popular as you can get, right? You know you've made it when they've named a potato after you. 1943, this was published. I found this book so readable. I found it a page turner, which is surprising for books about soil. And actually, by the end, I kind of had a micro crush on Lady Eve Balfour. And I looked her up to see if she was still alive, but she's dead. But I think she was a lesbian anyway, so maybe that doesn't matter. Anyway, none of that's got anything to do with it. She was at Reading University, or Reading before it was a university, doing crop trials. I think she did work in Kenya as well. She was the first person, I think, to describe and understand mycorrhizae fungi and understand their value and their importance. She did lots of experiments with pine trees, seeing their different growing impacts about the presence of fungi or not in the soil. Anyway, she was a bit of a pioneer. I think she had some dodgy political views, but you know, no one was perfect. But in terms of soil biology, this is great. So this book's so important. The Soil Association was founded out there to protect and enhance and to understand better the life in the soil. Lots of, yeah, probably can't see that. I think I've got actually a PDF version of this book, so I can make it available to you. Anyway, I was going to say, I think this is one of her pictures, one of her slides, or if it isn't, it speaks to her work. Thanks, Sean. So here's our little pine seedling. She did a lot of work on pine seedlings. And the brown, if you can see it, these are the roots of the pine seedling. There you go, like this. And you can see, look, it goes down to here, down like this. So the roots of this pine seedling are infused with mycorrhizal fungi. Look at these white, these nodes of crossing, these, this is what we're looking at, these structures within the fungi. Here they are, and from it going out, lots of the hyphae in different directions. It's a bit space age, isn't it? And the white is the fungi. So the surface area of the roots of this pine tree are being magnified by 1,000 times by the presence of the fungi in the soil. That's an extraordinary amount of surface area. And again, thinking about how roots might grip the soil and hold the soil particles together, how might the fungi then hold the soil together and grip the soil particles? Look how fine this just breaks down to finer and finer and finer branching pattern. In one of his lectures, Paul Stamets advances a theory, a calculation that he says in healthy topsoil in a forest, a cubic inch, so what's an inch? 3 centimeters. So a cubic inch, something like that, might contain 8 miles of mycelium. Mind-blowing statistic. 8 miles of mycelium in a cubic inch of soil. That's pretty awesome. So again, think about surface area, think about edges, think about nutrient exchange, think about soil stability, preventing erosion, and also think about how much disturbance you might cause were you to plow that. How much work has the soil structures, as the microbes, organisms within the soil, how much work have they done to create that web of complexity? So within that, now we talked about these little micro cavities within the soil. Think about the micro cavities within the mycelium, within that mycelium environment. Creates lovely little pockets where yeasts and molds and fungi and things can hang out and again form relationships, can either work with the digestate of the fungi or you're swapping nutrients with it in different ways. So it's very, very interesting to think about this complexity within soil and to realize, again, I think that's giving you a real empathy for why we try to do minimum till, why we try not to disdamage and disturb it, and also why we value the air. These spaces within the soil are so important. Okay, we're going to go down into the food web of in the soil, and look at. Also, I'm going to just check in on the term and think about trophic levels. So I want to think about that ecosystems have, and by trophic levels we mean energy levels. So there's always going to be the most matter in a system is going to be at the first trophic level, because the only energy coming in from the sun, that energy of the sun is translated through the plants, roots and shoots into organic matter. So the amount of organic matter in a system, including the living organic matter and the dead stuff, the waste, residues and metabolites from other members of the ecosystem, is always going to be the most amount of biomass. There's always going to be more of that than everything else, because everything else is secondary to that. They're further down the line. So if I'm eating secondhand energy as a fungi or a nematode, I'm not going to translate that energy 100% efficiently into my body. So there's going to be less biomass, less dry weight of organisms on the second trophic level than you get on the first. Okay, we'll finish exploring this after we've had our 15-minute break. It is now 10:29, so that's pretty good. And I'll see you at 10:45. Okay, and any questions or feedback, I'll handle that then. And I've got the builders around, so I've got to go and chat to them as well. So I shall pause the recording and break. Just before we went to the break, we were talking about trophic levels, and the ecosystems tend to form what we call a trophic pyramid, that the amount of biomass is always going to be more at the bottom, and as we get higher up, there's less. So we'll look at this again in another lecture, but we start to think about the shape and structures of ecosystems. So all the work, if you like, the real producers, the creators of new matter, is happening right at the beginning part. The plants photosynthesizing, translating the solar energy into the soil and using it to build their own biomass and bodies. And think then about how all these sugars and all of the other things that the plants are bringing into the soil then go out to the bacteria. We're seeing also how organic matter, the waste and residues from previous processes, are also being eaten by the bacteria and processed by the fungi. So fungi are building a direct relationship with the roots of the plant. And then we've got other root feeding organisms such as nematodes, microscopic worms. So this is our first trophic level, is the organic matter, the plants. And then second layer, trophic layer, so it's going to be slightly less in terms of biomass, are the decomposers, mutualists, pathogens, parasites, root feeders. So some of these plants might be parasitizing the living plants, some of them might be disease organisms, but also some of them are mutualists. They're symbionts. They're working in harmony with the plants. And also we have decomposers, these saprophytes, the things that break down dead matter and make it then available to plants again. So there's a tremendous amount of invisible activity happening between the first and trophic level components. The next layer, our third trophic layer within the soil horizons, is shredders, predators, and grazers. So grazers, the things that are just, if you like, enjoying the organic matter, the exudates from the organic matter, and any other sort of products or byproducts, they're eating that. Shredders are the things that are breaking up complicated organic molecules and simplifying them. And great, well, we've got shredders. Predators are the things also is, say, some of these things are eating, predating on the bacteria or predating on the fungi. So things like protozoa, amoebas, ciliates, flagellates, nematodes, nematodes feeding on fungal and bacterial feeders, and arthropods, little beetles, little things. I already mentioned, I watch woodlice a lot. They're fascinating things. In our slow, cool composting heap, it's full of them. And they seem to do a lot of the work, the shredding, breaking down leaves, breaking down, well, we have a lot of cardboard in there. And you can see from their droppings and things that you can just see how they're energizing and feeding the system. So all of this is kind of happening invisibly, because all of these are like tiny little things. So it's not until we get to the fourth layer, we'll see bigger worms, other predators, nematodes, bigger insects, the visible things, these higher level predators that are feeding off everything that's come before them. And then, of course, we might have mammals at fifth level, birds, and I've got a mole there, look, all sorts of other small voles and shrews, a very, very important part of the relationship to the soil. I'm sure I read somewhere that a vole eats something like twice its body weight in food every day, with a very, very high metabolism, and they breed very quickly. They're very active things, and they're burrowing through that the mulch layer all the time, chasing after all of these things which they're eating, and also helping accelerate the breakdown of the organic matter. So all of these elements, all of these individual elements form a system that is maintaining long-term soil fertility. So important. And so we can't really separate healthy soil from all of these elements. This is the ecosystem that creates and maintains soil. If we lose the birds and the mammals, the system is much, much, much weaker. And that will compromise the long-term health of the soil. Think about this as birds love to eat insects and seeds. Insects and seeds have a lot of phosphorus in them. Birds concentrate together phosphorus, and then they deposit it back in the landscape again through their droppings. So birds are drivers of the phosphate cycle. So we've got nitrogen-fixing plants, and we've got creatures that, we've got plants that accumulate phosphate, and then we've got other elements in the system like the birds that distribute it through the system again. So think about how all of these things might work together to create and maintain long-term soil fertility. Absolutely key. It's teamwork. And as a gardener, as a farmer, as an environmentalist, as a permaculturist, you're trying to consciously interact with this ecosystem. You're trying to understand how important this system is and build relationships to it. It's not the life, and we are partnering with life in the soil. Let's go back to Jeff's quote. So there we go. 5 trophic layers just within the basic soil biochemistry, and we could probably add many more things to this if we were to think about it more deeply. I think we've made our point. So this next slide is about the composition of soil. So I think if we were to make our recipe, there's things that we've touched on now, which we should be happy with. So what's soil made out of? Well, we know it's minerals. It's mineral particles, sand, clay, and silt. It's space. It's pore spaces and room for gases and gels. It says here. That is, let's go back a picture or two. What is soil made out of? Oh, what's that one I'm looking for? There it is. What is soil made out of? Well, it's mineral particles. Mineral particles. It's living matter. Living matter. It's also dead matter. Dead organic matter. It's water, air. It's roots. It's humus. And it's the living things, this stuff, the stuff that we've just been talking about. It's this stuff this is what we call the soil biota, the living components of the soil, the fungi, the nematodes, and all of the other stuff. So 1/3. So this is again from Bill Mollison's Permaculture Design Manual. This pie chart is the composition of an average soil. What defines as average, I don't know, but we're happy with that because we're interested in patterns, not detail, anyway. So, of the minerals that makes up 100% of the soil, it's only 30% by volume is the actual minerals. So there's a lot of other stuff in soil. In this average pie chart, the space, the air, is 40%. So by volume, we've got more air than minerals. Humus and roots joined together here, 12%. The soil water, available soil water is 11%. And the soil biota, the life, anything up to 15%. So we've got between the humus and the soil biota, the living part of the soil, and or the processed and sort of dead part, is anything up to 24%. It's a quarter. It's a lot. So this healthy topsoil is 1/3 minerals, 40% air, a quarter life and dead stuff and living stuff, and about 10% water. It's a very interesting mix. Let's look at these other two quickly. This one is the composition of a garden loam with mulch and a rich soil biota. Arranged proportions from wet peats to compacted mineral soils is given in brackets. Okay, obviously we're going to get huge variation because there isn't really no such thing as an average soil. Here's a good garden loam in which we've got much higher humus content. Or have we? This one says humus and roots 12%. It says humus 12%. Biota 8%. Slight difference. I don't really know why. And here we've got another one, estimated topsoil volume. Look, if we look at all of these, there's this one, this topsoil here, it's interesting, is 50% air, only 10% minerals, 10% water, and 30% organic content. That's the roots, humus, and the biota all kind of joined together. So, and I like to think about this third one a little bit, in that it's saying that healthy soil is 50% air. So here's an interesting thing, isn't it? This is one way that I look at this is the planet Earth is a ball of rock. It's hollow inside, there's some hot stuff inside, but it's a ball of rock. And then on the outside of that ball of rock is air. The soil is 50% rock, 50% air. It's 50% life and minerals and 50% air. So it's an edge, isn't it? The soil is the edge. It's not solid rock and it's not solid air. It's somewhere between the two. And I think what we're seeing and understanding is that perhaps the most valid and important and relevant variable within soil content is the air, and how we manage soils is how we can regulate that, how we can work with that. And it seems that the constant return of organic matter is key to that process, because the air spaces, if you like, are being opened up and maintained by the soil biota. There's a very interesting relationships going on between this living part of the soil and the air spaces within it. So again, as if we add the pore spaces to the soil biota, we get a 50%. And we can, so a very good humus, a very healthy soil with a humus of 12%, to be honest, and to get organic content up to 30%, that's very high. I think farms talk about having 5% or 6% organic matter in the soil. So, but there's a difference between farms and gardens. With farming, we have to do processes, if you like. With gardening, we can do a lot ourselves. We can make compost, we can add mulches and things like that. So we can have much more attention to detail in gardening. As the scale goes up, it makes it much harder to do those kinds of interventions because they're very intensive. Okay. Here are 3 test tubes of soil. Each one contains a grass. I think it's a maize plant, looks like. The only difference between the 3, they'll plant the same seeds, planted at the same time in the same soil. The difference is compaction only. So this is a heavily compacted soil. This is a very loose soil. This is in the middle. So we can see the root structure's only penetrated about this far down, and the plant's very stunted and weak. Whereas if we contrast it to this one, is the roots have not only is a significantly more root mass, is that root has greatly penetrated the soil to really deep down as well. So this plant here, or these plants here, are doing significantly better because they have a massive, significantly greater root mass, and that surface area is what's feeding those interactions. So very simple rules that come from this sort of analysis is: don't stand on the soil, and keep it covered, and keep it fed, and it will be constantly moving in a direction that you want it to go in. It will be improving its aeration, it will be improving its structure, and we'll be getting more and more soil life into it. Now we'll look specifically at composting and composting approaches in a separate class, but obviously the relationship to those inputs that you're putting in is the long-term health and fertility of your soil. This is about the next slide. It's a little bit complicated. And again, you see it in all of the soil science books. And these are the key nutrients that plants need. NPK, nitrogen, phosphorus, and potassium. I'm going to draw a little drawing if I can. I'm just going to let me do a little drawing. Okay. This is how I was told to remember the NPK thing. I'll see if I can draw it for you. Let's go green for this. Okay, so here's the leaf of a plant. Here's its roots. Here's the stem with a flower. Okay, hope that makes sense to you. A little simple diagram. N, P, K. These are, plants need this, these are the core nutrients that plants need, the base nutrients. They need all of these other things in micro quantities as well. But the most important for the basic structure and health and well-being of the plant, basic development of the plant, are these first three: nitrogen, phosphorus, and potassium. The chemical symbol for nitrogen is N, and the nitrogen is for the leaf. It's for the green part of the plant. It's for its structure, if you like. So you can imagine when your tomato plants are growing, that vine, that green vine is growing, you feed it with high nitrogen feed. You might make a liquid feed from nettles. You might just have a good high nitrogen compost, or you might have well-rotted manure. Those are really good sources of nitrogen. The P, the phosphorus, is for the roots. The phosphorus helps the strong and healthy root development of the plants. So if you've got leaves, I can't write with this, leaves, roots. And the K, the potassium, potash, is for fruits and flowers. So as our, let's say we're feeding our tomatoes with a liquid nitrogen feed to build the structure of the plant, as it starts to move towards its flowering cycle, we want to switch to something with high in potassium. And something that's high in potassium is comfrey liquor. If we grow Bocking 14, that comfrey plant that doesn't set seed, harvest the leaves, rot them down, feed them to the plant. There we go. There's the K. Wood ash holds quite a lot of potash as well. So we can save the wood ash from our winter fires. Don't put it on the ground in the winter because they'll just wash away. Save it for later in the year. Add small amounts. Bearing in mind, it's quite wood ash can be alkaline. It's going to affect the pH of your soil a little bit. But just spreading a bit on the ground when plants are starting to come into flowering is going to make this. That's going to support that function. It's going to help it. So NPK. Those are your key plant nutrients. There are many other nutrients that plants need: sulfur, calcium, magnesium, boron, copper, iron, magnesium, molybdenum, zinc, all sorts of stuff. Okay. Now, what this diagram is telling us and is pointing out is that in certain kinds of soils, what's the difference between these two soils? Influence of pH on availability of plant nutrients. So, okay, so this is a soil that's mainly minerals. This is a soil with a lot of organic matter in it. So as the pH of the soil falls, the availability of key nutrients also falls away. So you might have a soil that is showing nitrogen deficiency. Your plants may look yellow and weak, and you might think, oh, it's short in nitrogen. But actually, when the acidity is very low, when the pH is low and we have an acid soil, the nitrogen that is in the soil is not available to the plant. That's different from it not being there. And look how in our mineral soils, at 7, at a neutral, all of the nutrients are fully available. As we go into alkaline, some like iron become unavailable. And as we go low and acidic, some things like nitrogen and phosphorus and potassium become much less available. So we can see in strongly acid soils, even if there is a lot of nutrient available, it's not available to the plant. Okay, this is a more organic soil, one that has got more organic matter in it. And the wider parts again show the maximum availability. So again, as it looks like to us that we're getting the best availability of nutrients at just about 6 or something like that, just ever so slightly on the acidic side, it does best. And as we rise above, certain things become unavailable as the pH rises. So the constant return of organic matter gives us soils that are ever so slightly acidic, and in that our nutrients are more fully available. So there's a relationship between the pH of the soil and the availability of the nutrients in it. It doesn't necessarily mean that they're not there. It just means that the plants can't access them, and that's a difference, and that's a factor we need to think about. Okay, hope you enjoyed my little diagram there. I'll get rid of that. Oh no, I didn't mean to do that. Sorry. Okay, on we go. Here's our transect across the valley. On this side, we have permeable rocks underneath. So the rocks here, underneath here, are permeable. Water can percolate in, and water might percolate in, and then we might be getting out springs and things coming out further down the valley. Look, here's our convex slope. Here's our concave slope. Again, that shape that we talked about. It's a bit exaggerated in this picture. And then here's our valley bottom. So up on a on a permeable rock substrate, rainwater here doesn't stick around, it can soak into the rocks. So we might get a thin, skeletal acid soils, but they're quite dry. As we move down through the slope, we get the red-brown soils. These are the good soils for farming. We often see a lot of farming on these sort of slightly lower slopes, let's say down here. And then in the bottom of the valleys, what it's saying here, we might have an alkaline soil because it's well drained. And in the impermeable substrate, it's going to be, I don't understand that. It's saying deep peats, sometimes alkaline. I would expect it to be acid. Anyway. So peat, what's peat? We've just got a mentioning about what's a peat soil. And obviously here, this is impermeable. So when it rains here, that water cannot penetrate. So we have a lot of stored water on the hilltops. So that means that it becomes anaerobic. There's special kind of grasses that grow in that kind of soil, but they can't biodegrade because there's no bacteria, because it's anaerobic, because it's wet. So what happens is that the organic matter breaks down to a certain point, and then it sort of pickles itself, and then it grows on top of itself. So that's what a peat soil is. It's sort of pickled carbon, and peat soils are very important carbon stores, and there's something that we should not, under any circumstance, be interfering with. A lot of what they do in Wales, or have done in Wales in previous decades, is they've drained these uplands. They put lots of land drains in so that the soils become less acidic, and then you can plant pine trees in it and do monocultures of forests. So that is destroying a long-term stable carbon sink, a very fragile, very specific biology of plants that like to live in those conditions, and then replacing that with a monoculture. And at the same time, we're draining uplands to accelerate the flow of water downhill because we want to cultivate up here. So what does that do? That causes flooding. And what we're seeing now more and more and more is flooding in the lowlands, flooding in the valley bottoms. Oh, these are the places that we've started to build on. And when we get flooding in valley bottoms and places where people have built houses, then they always say, can't we have drainage? Can't we accelerate the flow of water downhill even further, even faster? So then that's draining out the uplands and creating even bigger floods further and further down the system. So there's an awareness and a thinking about the conditions change as to where we are within a bigger system. Now, this is a very steep valley. Most valleys don't really have that much steepness to it. They're much more like this, especially in the lowlands. But there's a difference. There's a changing of conditions, and we move from the top to the sides to the bottom. And obviously, in the bottom, often, actually, we end up with very clay soils down here because the smaller particulates wash out. The heavier ones are more likely to stay where they are. The lighter particles wash out, and we have deep clays usually lying, in the lower lands. When you come to Llanfyllin, and I show you where our community garden is, you'll see that's a very clay-rich soil there, and it's a river bottom. So conditions change as we go through a landscape, and we have some very specific and valuable types of soils that occur under very specific conditions. Okay. So we'll have a little look at the overall picture of the carbon cycle, and then we're going to move and look at a little bit of water. This diagram is quite out of date, but it's a good reference point. This is from the 90s, the carbon cycle in the 90s. So firstly, if we just cover over, let's look at the forest bit, understand that. As forests grow, they pull in a lot of carbon. That carbon is the structure of the tree, the leaves, the caterpillars, the birds, everything that's in that ecosystem. all of those, so it's, the forests are pulling down a certain amount of carbon out of the atmosphere every year, and that's part of the natural carbon sequestration, the stacking away of carbon into the land. And as a forest, I've already touched on this earlier when we talked about succession, but as a forest approaches maturity, the amount of carbon that it's stacking away starts to approach neutral, because it's built now over time. It's sucked loads of carbon down, it's built a nice rich soil underneath it, and then it reaches a point as it gets older, climax, that the forest is kind of dying at almost the same speed at which it's replacing itself. So it's dropping leaves every winter, but some of those get incorporated into the soil. Some of that also goes back into the atmosphere as it gets sort of oxidized and if you like. So there's a net sequestration under established woodland, but the amount that it sequestrates slows down as the woods evolve. Now, in terms of fighting climate change, that gives us an advantage, is that we've created lots of bare land. If we could reforest that, we could have a big gain very quickly in terms of carbon capture. Really, for long-term stability, we want to get that into the soil. So let's say, as of 1990s figures, that the forests were net sequestrators of about 6 billion tons of carbon. In the oceans, it's about the same. We've got lots of algae, and then there's lots of things that predate and eat that algae, little diatoms, little microscopic sea creatures that have a calcium carbonate shell, and as they live and die, that precipitates out into the bottom of the sea, and that's what forms chalk and limestone deposits and things like that. And again, that represents a sequestration of carbon into the oceans. And over time, the oceans are also a net sequestrator of carbon. They pull down 338 gigatons and they return 332 gigatons. So there's only a 6 gigaton sequestration effect, but again, it's a part of an enormous cycle. But there's a thing that's happening, is that as CO2 rises, levels have risen in the atmosphere from 275 to 407 parts per million, is the amount of carbon going into the ocean has increased, but that is changing the acidity of the ocean. It's changing the pH of the ocean. The more CO2 the oceans pull in, they start to become slightly acidic. And that is a problem if you're an organism with a calcium carbonate shell, because it's going to dissolve. So this is why this acidifying of the oceans is destroying the coral reefs. It's an enormous threat to the life in the sea. And as we move forward in our climate action, we realize that we have to accelerate and work with the sequestration of carbon on land and in soils. I've heard it postulated that we could possibly lock away 100 billion tons of carbon in the soil each year if we manage the whole global ecosystem to that effect. So I don't know if that's true or not, but certainly these are very, very important ideas that are worth exploring into. So of course, net sequestration on land and net sequestration on sea. So over time, over the last 10,000 years of stable climate, the Earth has stacked away gigatons of carbon. Really, 10,000. So if it's 6 billion tons a year, multiply that by 10,000 years, stable Holocene climate. That's a lot of carbon. Some of that carbon, the fossilized carbon, we're digging up and burning, aren't we? The coal, gas and oil. It's interestingly that the coal, gas and oil formed in the Earth's crust between 60 and 30 million years ago. And that happened at a time when there was no bacteria that could break down lignum fiber. So the tough bit, the polymer, the tough thing that holds trees together, there wasn't anything that could break it down at that point in terms of evolution. So the ancient forests became pickled, and then they became compressed, and ultimately became coal, and the microbes became oil. And that process stopped 30 million years ago when new microbes came along that could break that down. So there's no new coal or oil being formed. So that's why it's a finite resource with only so much of it. We've burnt our way through about half of it, and we've created a global economy that totally depends on it. And we're now confronted with some of the starkest and most difficult choices that we've ever had, because this energy source that we're relying on is becoming harder to access and harder to bring to market. And the impact of burning it, this 23 gigatons from fossil fuel burning is now more like 35 gigatons from fossil fuel burning, or 40 gigatons is our total emissions. So this is going up and up and up. As we erode into the forests, this is going down. As we acidify the oceans, their ability to absorb carbon is going down. So the climate problem is climbing up and up and up in terms of its total impact, because the ability of the Earth to sequestrate and absorb the surplus carbon is being diminished every day. And our keenness to push out emissions is growing. You know, we're back, global emissions are now back at a rate higher than they were before coronavirus started. You know, we had a little brief break, but it didn't last long. People have gone back to burning stuff again. Somehow, I don't know how we break out of these behavior patterns. We absolutely have to, and we are, you know, against time's not our friend. Okay, so there's your big carbon cycle. The take-home message from this is the repository for long-term carbon is the soil, and we need to work with this process here and make interventions and interactions. Yes, we need to grow more trees, but we need to manage those trees in which that carbon translocates into the soil and becomes a long-term carbon store. What strategies can we do to do that? Well, watch this space. We'll be talking about that as we go forward. Okay, so there you go. There's our little introduction to soil. I hope that's got you going. And we're going to move to water. Can't really understand soil without understanding water, and these two things interact in so many ways. Really worth getting to grips with this. So basic geography lesson. We already touched on this sort of physics. Water flows downhill. It's quite important. And the other bit of physics that we need to be aware of is warm air rises. Warm air is less dense. Warmth makes the molecules move around. And so it makes the air less dense. So I have been corrected previously by students to say, actually, warm air doesn't rise. Cold air sinks. Cold air sinks and pushes up the warm air. Okay, you win. I got it wrong, but I like the warm air rises thing anyway. So as long as we understand what we're saying, that's what matters. The sun is shining onto this landscape. The sea represents an enormous thermal mass. That water is like a heat store. It's like the storage heater, the bricks in your storage heater. Okay, so the sun shines on the sea. The sea is very big. The ocean is vast. Sun shining on it, and it's deep. The sunshine warms the water very slowly. So the average temperature of the water rises slowly, and then it falls slowly again, day and night. So that's one kind of heat process. The sun is also shining on the land, and the land heats up more quickly. Right, temperature rises more quickly and also falls more quickly. So during the course of the day, you get a pressure differential between the land and the sea. Let's say towards the afternoon, the land is warmer, so warm air is rising off the land, and it's had a chance to raise up, and it's going to flow back over the sea, and the water on the sea maybe is a little bit cooler. And then maybe it's the other way around. Anyway, but what I'm saying is, but it takes long enough, as long as there's enough heat towards, so we go sort of into the day, the sea gets warmer, and then towards the end of the day, the seas have the maximum heat gain, and the land's starting to cool, so we get a convection current going this way. Is that the warm air is going rising and start moving over the landscape, and the cool air, as it cools in the evening, is going to flow back down into the sea. So we've got a conveyor belt bringing water vapor over the land. That's basically what we can see. Obviously, this might vary according to weather patterns and clouds and what have you, but you can see how the fact that the one heats up slower and than the other means there's going to be a pressure differentials happening at different times. So we kind of guaranteed a flow of water vapor coming over the land. Okay, so here we have warm air that's saturated. There's got a lot of water in it. The Earth's total water supply is estimated to be over 1.3 billion cubic kilometers. It is constantly redistributed by a variety of processes. Water evaporates from the ocean and may fall as precipitation over land. Water re-enters the atmosphere from the land by evaporation and transpiration, water lost by plants. Water flows from land to ocean in surface, rivers and streams. It also travels through the soil and rock as groundwater. There is 30 times as much fresh water below ground than in lakes, rivers, and inland seas. There we go, a few little facts. Okay, let's just think about this now again. So water vapor is traveling over the land because the land is rising as we go away from sea. The air is pushed up higher, it's cooler higher. As warm air rises, it also starts to cool down as it reaches the higher atmosphere. So it's moving around less. So the water droplets, the vapor in the air starts to stick together to make water droplets, which makes clouds. And eventually when those droplets get too big, they fall down as rain. So you can imagine the rain's covering the whole landscape. And some of that rainfall is going to land on plants, and it might just evaporate from the plants again, go back into the atmosphere. But it's also going to trickle down, isn't it? It's going to penetrate into the soils and humidify the soils. We've got 30 times more water below ground as we have above ground. So that's always going to be an interesting thing. But the most available sources to work with are those above ground. So we're going to talk about that too. Pumping water uphill is expensive, and you're essentially working against physics all the time. So if we can, and don't forget, new rain is always coming from above. So we ought to be able to, in terms of catch and store energy, the higher in the landscape we can catch and store water, the more potential energy it has, the more useful it is to us. Once it's down in the sea, it's no good to us at all because it's saline. Also is, even if we could remove the salt through some kind of desalination process, it's still at the bottom of the system. We've got to transport it uphill. That's expensive. That's resource efficient. That's resource inefficient, resource hungry. So imagine every surface is being covered in rain. Some of that flows over the surface very quickly and gathers into little tributaries, rivulets and streams, which eventually form our watercourses. But a lot of it will just soak into the soil. A lot of it will even percolate down deep into the subsoil or right down into the bedrock. So there's different routes it can take. But eventually gravity is always going to do its thing, and it's going to slowly return back into the wider system. Okay, so there's our quick look at the hydrological cycle. And of course, high up in the mountains, some of that rainfall is going to arrive as snow or ice, and it's going to be locked into that system long term in terms of glaciers and snowfields. And glaciers and snowfields represent a long-term storage of water high in the system. They're very, very valuable. And because obviously when we get seasonal snow melts, that feeds rivers and tributaries, and a significant proportion of the world's people depend on sources of water that come from glaciers, that come from big stores of frozen water high in the mountains. Think about what maintains maybe the big rivers come out of the Himalayas, the Ganga and Jamuna, and so forth. South America too, rivers that flow out the Andes. So as climate change progresses and we lose these snowfields and glaciers, it's going to make many cities unlivable because they're going to lose their water supplies. So this whole system of these amazingly complex systems are being compromised as we change the climate. So these are slightly more sobering things to keep in mind. Okay, next. So it talks about here, what was it? There's 1.3 billion cubic kilometers. It's very hard to imagine that. I don't know what 1.3 billion cubic kilometers really looks like, but anyway. Of that 1.3 billion cubic kilometers, 93.8% is in the ocean. So 94% of all of that is already, I've told you, out of commission, really. Nearly 2% is locked up in glaciers and permanent snow, and 4% is in groundwater up to 5 kilometers deep. So that's 93.8 plus 2, that's 95.8, plus 4, 99.9. 99.9% of all water is either in the sea, in the ground, or in snow. There's very little of it is in active exchange at any point. So us, 7 billion people, and all the other organisms on the planet, we're all sharing 0.1% of that, whether it was however many cubic kilometers. We've only got a bit. And of that, only so much is available. Here's the figures again out of Bill Mollison's Designer's Manual. The second set of figures are about fresh water. So fresh water is only 3% of all the water, and 75% of that is locked up in ice and glaciers. So of the fresh water that's available, 13% is more than 800 meters deep. That means it's out of reach, and we can't get at it. 11% is in groundwater up to 800 meters deep. So again, it's a very small amount is actually in the lakes, in the soils, in circulation, in atmosphere, and in our bodies. So water is so scarce. Water is it's constantly in cycle though. So again, is if we simplify landscapes, if we remove the upland forests, if we drain the peat bogs, if we build cities and roads and drains, and we compact the land, and we use farming techniques that compact soil, remove ground cover, all of those actions are serving to speed up the return of water back to the oceans. So everything that we do that's about what we think we're calling flood control or drainage or cultivating land, building towns and roads, any kind of development, essentially serves to accelerate the return of water back to the oceans. So development dries out landscapes over time, and this is having a long-term impact. And this is, again, something that we need to think about big scale and small scale to work against that. So everything within permaculture and water management is about trying to catch and store and hold the water as high in the system as we can, and to use biological storage in soils, in plants, in mulch, in compost, in organisms. All of the, your body is physically 70% water. Most other organisms are the same or similar. So if we've got big populations of forests and bears and fish and birds up in our mountains, that represents the storage of water where we want it to be, not in the ocean, on the land, and high up in the system as possible. all this draining and management and farming and so forth, development is just drying out the whole landscape. And then, interestingly, when you have a dry landscape, that landscape is not ready to receive rainfall when it comes. So when you have dried out arid landscapes, they also come with flooding. And so when it does rain, it becomes a deluge, and again, it washes away a lot of the topsoils and accelerates the drying out effect. So flooding very rarely, floods and heavy rainfall very rarely replaces a deficit. We've had years of drought and then we have massive deluge. That doesn't cancel the drought. It doesn't necessarily replenish the groundwater and the streams and the springs. That water just cascades over the landscape, returns to the sea very quickly. So these are further considerations. So when we look at planet Earth and we see the globe, or we see the pictures from spaceships or whatever, it's always blue. And we're called the blue planet, the blue marble, the blue planet in space. And we know that the oceans are really deep, and ocean trenches 2-3 miles down or something like that. Crazy. But when you know that the planet Earth is 13,000 kilometers across, and the ocean trench here is only 3 kilometers, you realize the ocean isn't deep like you think it is, because compared to the rest of the Earth, it's a thin film of water on the surface. It's not this enormous resource that we might, in the way that we think of. And if you were to put all of the oceans into like a snowball, into a sphere, scrunch it up, relative to the size of the Earth, it would only be this much. So it's like back the idea of this layer of cling film around a rock. It's much narrower and shallower than you might think. And this little blue dot, that's the amount of fresh water at any one time. So even think of all the Great Lakes and huge rivers and the Amazon basin and the Congo basin and so forth, it's that much water at any one time. It's in constant circulation. So interesting thought. So we have to value water with much more reverence perhaps than we do. And one of the greatest wealths and assets that we have here in the UK is we have quite a lot of rainfall. It's so valuable. One of the reasons I chose to come to Wales, well, many reasons I chose to come to Wales. I only come from Shropshire, not from very far away. But having lived in Zimbabwe, having lived in more arid areas, I recognize the value of the water that we have. Bill Mollison says in one of his books, in the future, we will value land not by its size, but by how much water it has. Water's the greatest resource, and it's almost the ultimate limiting factor. You can have 1,000 hectares of land, but if it has no water, it has no value. And okay, places like Saudi Arabia and the desert in Saudi Arabia, they sank loads of boreholes. They found there was mineral water deep down under the desert. They'd pump it to the surface. They did agriculture. They grew a lot of weeds in places. They managed to rebuild the fertility. But that water, that mineral, that water layer in the ground slowly gets ever deeper and harder to reach. And you have to make your boreholes ever deeper, more and more expensive, and eventually the whole system breaks down. So just going after groundwater isn't in itself a total answer, because we eventually lower the water table. So we need, as much as we can go after water from the water table, for groundwater, we have to twin that with strategies to increase percolation into the soil, rainwater percolation back into the soil. And there's a lot of strategies about that within permaculture. So a lot of what we're trying to do in our bigger picture, overarching approaches, is we're trying to manage water very carefully. We're trying to look at whole landscapes and ask ourselves, how do we hold that water into the landscape as long as we can? How do we make it do the longest journey it can through that landscape so it can nourish and water as many plants? And how can we control the movement of that water through a landscape so it doesn't cause erosion? Because that's the other problem. Water, obviously badly managed, is an incredibly destructive force. As we simplify landscapes and lose forests and lose diversity, then we're allowing water much more of a free rein to cause damage if we have, extreme weather events. So all of these are very, very, very important considerations, and a good long-term thing. Right, okay. Here's go back to our slope again. We keep going back to this idea about slope. Flatter at the top, convex, the key point, the bit where that change point, that inflection point where we move from convex to concave, and then here. So once we get past this key point and we get to a slope that is now going above, certainly if it's above 18 degrees, and this example it's saying above 12 degrees, is this needs to be forest. These upper slopes need to be forest. We can work with the tops of the mountains, the ridges and skyline, to enhance catchment, because we get much higher rainfall higher up in the landscape. And that's for the very simple reason that the higher the clouds are pushed by the landscape, then the more the water particles condense, and then the more likely we are to get rain. So water catchment high up in mountains turns out to be important. And then once we get onto these upper steeper slopes, it's very important that they are forested, because that's also part of the water catchment, and it's part of the humidification of the whole landscape. So once we get above about 18 degrees of slope, we want to have forest. The key point is that inflection point in the middle, like I said, and often we have settlement around this point, because also as we start to get wells and issues and springs start to form and be available here. So water that's percolated into the landscape here starts to become available as we get a bit into the lower slopes. And we have this very important part here between the key point and the bottomlands, which is where most of our farming land is. If warm air rises, cold air slumps. So we can also think that cold air is heavier. So if we have a cold day or cold air forms high on the mountain, it's going to travel down the slope and sit as a frost in the bottom of the valley. You can have cold air might pass through these places, but it's not until it gets to the bottom that it sits and causes a frost. So we can do lots of interesting farming on valley bottoms, but also they have very specific weaknesses. It tends to flood and it tends to get frosts, depending on the details of the site. But again, it's all about observation, right, to understand these things. So we can have long-term storage of water higher up in the slopes, and then as we come down to the lower slopes, we're revitalizing that water by working with it, allowing it to go through streams and re-aerating itself, go through living systems and plants and so forth. Okay, again, this diagram's from Bill Mollison's Designer's Manual. Okay, back to the hydrological cycle again. We're going to just revisit that diagram. It's one slightly structured differently, and just to get the understand these processes. Excuse me. Understand these processes a little bit more differently. And I'm going to enlarge on it again as well, because this is so key. So as evaporation and transpiration, humidifying the air, and there's some of that is falling as precipitation. And I guess the rest is going on higher into the system as we climb up into the into our system. So on the steeper slopes, we have trees. when that rainfall lands, it's going to hit the trees. It's intercepted by the trees. So instead of it hitting the ground with a erosive force, the water droplets hit the trees and they shatter into like a mist, and it gives it takes out the kinetic energy, the force, the momentum of the raindrops, slows it down and makes it more like of a mist. So it takes away those erosive erosive force, and can soak into interact with the trees and sort of soak into the soil. Now, I told you that 3 inches of leaf litter, 3 inches of mulch can store an inch of rainfall. And so think about that, especially that above ground storage is so important, because that allows the slow percolation of groundwater into the soil. Now, some of that might flow into a surface storage, into ponds. They might be constructed by you as a dam or a strategic thing, or it might just be there naturally. But there's going to be infiltration and seepage into groundwater. Now, some of that groundwater is what we might call a through flow. It doesn't go very deeply. It's going to travel through the topsoil, nourishing plants. It might come out as a spring at some point. It might join a stream, and it might be overland flow as well. There's what we call interflow. There's water that goes into to bedrock level. It goes through the soil and reaches the bedrock, and it comes on a deeper return. And then there's also what we call base flow. There's water that, given the time and the opportunity, will seep deep into the landscape. And this is what replenishes those long-term groundwater stores. So especially if we're extracting water from groundwater, if we don't replace it, the water table is going to be going down. And the ability for water to reach deep down in the system is all to do with how it's managed higher up in the process. I want to show you a 7-minute video, actually, and then we might just have a very short break after that, just because we've it's all I'm just going to allow me 1 minute. I've got it posted somewhere, but I'll find it on YouTube. Sorry, I'm just looking for something specific. I've got it bookmarked and things. I just thought I'd find it quickly. Of course, I haven't. It's annoying. Okay. Okay, just give me 1 second. Sorry. Oh, so no. Okay, look. Okay, maybe what we'll do then is we'll have let's just have a 5-minute break. I'll have a 10-minute break. We'll come back together at midday, and then we'll just do 1 more hour. So we'll just take a break now, and I'll find that. I'll pause the recording. I'll find that video for you. We'll come back in 10 minutes. We'll start again at midday. And yeah, thanks, Sean. Okay, see you in 10 minutes, guys. Resume recording. We're on it. Thank you. So yeah, beautifully nerdy video there. Just but such an important thing. He's explaining why we're drying the land out is because by removing plants, having bare soil, that when it does rain, the land can't accept and hold the water. As it cascades off, heading downhill, we're seeing more and more flooding in the lower lands. And it says the idea that to alleviate flooding would be to accelerate the water even faster, actually drains the land above it even faster. So all of our instincts really about how to deal with surplus water are kind of wrong. And in many of the interventions that we're making, it's making the situation ever worse. So let's think about this, because this is obviously the key thing that has to change kind of globally. I'm going to come back to this. This is our same slope again, really, we've been working with, and then thinking about how we might be able to store water high in the landscape if we have catchment up in, what do they call it, the ridges and skyline catchment up here, high dams, maybe shallow dams, we can hold water up here. Think then about how cold night air might fall in the landscape. So we've got, here's our steep slopes. Here's our steep slope above 18%, forested. That's actually going to have several ways that it impacts on the landscape. One is that it interflows with the flow of water, with rainwater, massively reduces erosion, and returns much of that moisture to the air as evaporation. Okay, and you can imagine also it's going to also condition and change the landscape, because as our cold light air falls and comes down through the forest systems, it's slightly warmed, and it gives it a chance of perhaps to rise off again, protecting our settlement at the key point of the landscape. And then we've got productive systems, farm systems. This is a food forest. And then as we approach to the bottomlands, we maybe have a low water storage again at the bottom to support other growing systems. So look, we've got three opportunities to store water. One is at the top of the system, high up in the system, maybe in the middle point, somewhere at the inflection point, and again at the bottom. So we can get yields from that water at different parts in the system. Again, this is the diagram I always want to take a bit of time to explore. And I think of all of our different thoughts about how rainfall and landscape interacts. We need to be able to think of it as the whole system. And again, is because we're always only ever experiencing a small part of the system, we're often not looking to the whole picture, which is again why we think that drainage actually might reduce flooding where actually it increases it, because we're only looking at one small part of the picture. Let's go right back to the ocean and think that we have evaporation, 7% of total atmosphere water. Evaporate, again, this is from Bill Mollison's Designer's Manual. This is some of the really, really wonderful illustrations in there that help bring these thoughts together. So think about water not as an individual event, or rain as an individual event. Think about water and rainfall as a conveyor belt, as a process that's continuously happening. Is water's evaporating off the sea, journeying across the landscape, and then returning through rainfall, streams and rivers back to the sea again. So we've got a conveyor belt of water. So if you think about it as a never-ending conveyor belt, if we can catch and store and slow down that water, hold it higher in the landscape, here, then we're humidifying the whole landscape. How can we make more and more interventions which catch and store water high in the landscape in a way in which it's going to humidify the whole landscape? These are things which we think about in permaculture. So look, here's our water vapor forming clouds, forming over the ocean. Prevailing winds coming onto land because of this pressure differential. It's bringing this, so we can think of this cloud, it's 100% evaporated seawater. There it is. And so it has a particular set of characteristics, and it's evaporated seawater. As that moves over the land, some of it is going to fall as rain. That rainfall is going to land on plants, it's going to land on the soils, and some of that is going to evaporate back into the air again. Some of that rainfall also will be transpired by plants, this evaporation from the leaves. And so in some ways, let's look at this sort of spiral pattern, this corkscrew here. Here's our moisture arriving from the sea, falling as rain, but then being re-evaporated and going back up into the clouds again. That water vapors condense around nuclei, around little particulates that might be in the atmosphere as well. And also we can say is that imagine this, that the trees, the surface of the leaves of the trees are covered in microbes. They're covered in bacteria. They're covered in bacteriophage. They're covered in the broken bits of dead bacteria too, little bits of DNA, little bits of, little particulates, molecules of living and dead organisms. Also get taken up by the water droplets and evaporate into the air. Some of those become the nuclei of future raindrops. These clouds now that are forming over this forest, maybe only 60% of that is that original evaporated seawater, and maybe a whole bunch of it, maybe 40% of it, is the re-evaporated forest water. That re-evaporated forest water rain is now ever so slightly different from the seawater because it contains different kinds of cell nuclei. It contains different kinds of little particulates with it, maybe dissolved nutrients even. So this flow of moist air over the landscape is actually interacting with the landscape and being informed and changed by the landscape. You can think about this rainfall as it falls and re-evaporates and falls and re-evaporates. It's being transformed by the landscape interactions that it's making. That's really interesting to me. Look, we're now kind of halfway into our landscape, halfway between the mountaintops and the sea, and Bill's suggesting that maybe at this point these clouds are 50% of sea origin and 50% re-evaporated rain. So think about how the landscape, a healthy, productive landscape, is creating its own rainfall. He says here, in these foothills and these low parts of the system, is if these trees are cut, rainfall might decrease by between 50 and 100%. So as we go into the system further, is already half of the rainfall is re-evaporated. So if we've removed those trees, there's just only going to be half the rainfall. See how we dry out landscapes. See how, as we simplify them for agriculture, as we simplify them for housing and industrial developments, is we're all the time speeding up the return of water back to the seas, and we're reducing the amount of re-evaporation that's going to go on to create the next, if you like, generation of rainfall. These are the fundamental errors that we're making in terms of our development, and that's because we've always taken rainfall for granted. Going back to this catch and store energy, this idea of appreciating these natural resources and not taking them for granted, and because they've always been there doesn't mean they always will be there. We fail to see where they come from and how it works. So as we move into the landscape, as we get further away from sea, we're more and more dependent on re-evaporated water for rainfall. In fact, we have this lovely word, evapotranspiration. I like that. So some of the water is evaporating off the surface of the plant, and some of it is actually being transpired by the plant. But we're getting this joint effect, which is actually returning. A lot of the moisture is now being returned to the clouds. So Bill's saying here, by the time we're getting like 85% of the water now is condensed into trees and mist in the forests. These trees are cut down, precipitation might decrease by 80%. And these clouds now, well into the system, are 100% forest origin, and they contain the organic nuclei and plant nutrients. This also represents information and nutrients as well as just water. So plants are communicating, exchanging important things. As we reach, so some of this now gets higher up, some of this might fall as snow. As we get high enough up, we might reach a state where the evapotranspiration is equal to the rainfall. And we get very, very special conditions high in mountains where we get a thing called cloud forest, standing cloud. If you like, the rainfall is equal to the evaporation. So it's like a permanent cycling of water going on, think about this, holds the water permanently in the ecology of the mountain top and the forests and in the clouds. We've got a permanent exchange. Again, these are some of the rarest, most valuable ecosystems on the planet, are the cloud forests, which you get high on mountain ranges. And as we reduce all of these systems before it, so then eventually we lose that cloud forest, and then we've destroyed the system essentially. This is the big picture overview that we need to keep in mind. And think about how, where you are in your landscape, how you might behave in a way in which you're taking this bigger picture into account. So look, there's a kind of a cylinder described here, and we're going to jump into the picture, just into that little bit of detail. So imagine here we are in this part of the system, and oh, here we got some pictures as well. Okay, so look, this is driving up through North Wales. It's just rained. The sun's breaking out. Look, the light's coming out again. And look, this is evapotranspiration. This is the moisture returning back to the atmosphere. Some of this rainfall didn't even touch the ground. It just soaked the trees, and the sun came up and it evaporates out again. So again, think about how plants are humidifying the atmosphere, how they're actually circulating that water, holding it in place, catching and storing, but also working with it, oxygenating it, aerating it, I say adding all sorts of maybe micronutrients and things to it as well. And then so if on a warm day, warm air rises, there's the moisture rising, and in the evening, as it cools, it comes back down again as dew. This is like what we would call dew, I guess, the condensation. And this is just the fact that as the air cools, the water droplets become larger and stick together, heavier, and they fall back down to earth again. So again, somehow we've got this thinking of the landscape breathing in and out, how the moisture is staying around because it's been constantly interacted with and energized. Okay, so now let's see that as a diagram. Here's our forest canopy. Here's our rainfall landing. So the total amount, so that's what Bill's saying is, of the water that's raining onto this forest, 25%, he goes for 25.6%. I don't know how he's got so accurate, but that's just interesting. 25% of the water that rains over this forest doesn't even touch the floor. It just makes the leaves wet, and when the sun comes out again, it evaporates off again. So again, think of that, holding moisture in a cycle just above the surface of the forest, evaporating off, and maybe condensing and cooling in the evening, coming back down, evaporating again in the morning. Water is being cycling, being reconditioned and energized permanently by the way it interacts with plants. So if 25% doesn't even touch the ground, then 75% does. So what happens to that? Well, 48.5%, pretty much half, is returned to the atmosphere through transpiration, taken up by the trees, evaporates off from the roots, from the leaves. So evapotranspiration returns 75% of water, okay, 74.1%, according to Bill, of humidity is returned to the atmosphere just by the action of evapotranspiration. So we have bare ground, we've got bare soil, we've got a nice plowed field. That 75% return might drop to 5%. I don't know what I made that figure up, but it's going to be significantly less. 25%, 25.9%, so Uncle Bill, to keep you happy, enters into groundwater, surface water runoff, streams, rivers. Okay, so here's such a key figure. This is probably the most important statistic of all in this picture, is evaporation from forest soil. How much of the total rainfall evaporates from the forest floor? Zero. None of it. Nothing. Fascinating. So when we've cleared lands and when we've exposed those forest soils to the sun, something starts to happen that's never happened before, which is evaporation from the soil. So mulch, 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 shade, 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 plant, plant, plant. Keep it, keep, you know, these are obviously the clear lessons that are coming out of it. Water is returned to the air by trees, helping create clouds. Transpiration, the release of water through the pores of trees and other plants, accounts for up to half or even more of all moisture returned to the air. So, so, so important. So bring this understanding together with the water cycle experiment, that little video that we saw before, and you start to realize how these things might join together. A bigger picture of understanding. Okay, so we got, yeah, okay, a couple more slides, which is about sort of living systems, and then maybe I might just make a couple of other small points before we go for lunch. Okay, so we'll go back. I touched on this already, but let's just think about this a bit more. Is how rainfall interacts with a tree. So here's our tree. Actually, I could do with a plant to show you something. Let me just find. What have I got there? That's not a very good example. Let me just 1 second. That's not quite what the example I wanted to look for. Anyway, sorry, I distracted myself. Okay. Many plants, you see, the leaves kind of sit like this, don't they? And what's happening here is, imagine there's a heavy rainfall. The heavy rainfall is hitting the tree. So the first thing is those big drops of rain aggregated together, lots of drops, heavy, falling from a great height. That represents an explosive impact. That can be very erosive, just the force of that rainfall. So when that rain hits the tree, the droplets are shattered apart. They become like a fine mist, so that the kinetic energy has been taken out of the rainfall, and now the water is trickling rather than having this velocity. Most leaves of plants are kind of balanced, and what happens is that when the rainfall first arrives, they tip the water towards the center. So often what happens to the tree is the rainfall landing on the tree is actually flows towards the center of the tree, just because the nature of the way that the leaves are set, and we see a through flow sort of down the trunk. Water's held in the bark fibers. It flows over the stems and there's channels the runoff, and if you like, the plant is harvesting and flowing that water to its core, where it's going to flow into the ground and nourish the roots of the tree. The heavier the rain gets, the more the leaves then start to tip over, so then the water flows away from the center of the tree. Once it's fully taken, it's taken its drink, the surplus flows over the crown, and you get what they call a crown drip. You get depositing water then around the outside of the tree. So again, maybe it's also the ends of the roots that now getting nourished and watered. So the tree's helping distribute how the water is dispersed over the ground, and then eventually sort of watering itself, and then also creating interesting microclimates around the edge of its canopy. So we now got this through flow of water coming down through the trees. And again, it might be washing nutrients and other useful things from the surface of the tree, dead bacteria, other organisms, and all of that again is returned to the soil. And then think about how that's going to be taken up by the soil, and it's going to increase the complexity and diversity of the soil, and therefore the nutrition of the tree. Also, it's pointing out that There's a surface evaporation, but that's greatly reduced by the leaf litter, that's holding water on the surface. And then also is, as this water flows down through the tree, the roots actually help it percolate and penetrate deep into the ground. So we get much better rainfall infiltration where there are trees and forests. Bare ground does not receive and infiltrate water well. And we saw in the video that the surface, once the surface water becomes saturated, even though there's loads of dry space below, then the water just flows over the top because it can't penetrate fast enough. Whereas in this, where it's interacting with the tree's slowing down the flow of the water, it's spreading it out, taking out its kinetic energy, creating lots of surface area. It's creating multiple ways into the ground for the water to percolate. These are all very important. And then, of course, also in this diagram, it's exploring the relationships at the roots. The water becomes bound on soil particles. It's almost like there's a little film of water around each soil particle. Again, using that surface area, holding that water there. And then also think about this fungal mycorrhizal storage. Think about that complexity of fungus is also absorbing water and transporting it through the soil, making it available in other places. Where we've got really good flow from this crown drip, Bill suggesting that might percolate in and replace the soil reservoir, that deeper down soil water that replenishes our wells and springs. So there's a complex set of interactions happening. It's helping translate that rainfall to take out its energy, spread it out over a surface area, and allow it multiple ways in to be held in moisture, held as moisture, and to allow it to percolate into the landscape in many, many different ways by different routes. So cut that tree down, create bare soil. Think how many differences you're making. It's multiples of difference. That's the significant thing, really. And here's down deep in the leaf litter. This is actually a pile of gorse logs, of sticks that are decomposing, and its mycelium are obviously breaking those. You can't actually see the sticks because there's such a crop of fungi there. But I was looking at this in this leaf litter, and it was literally someone was doing this for soil building, and I looked at, and I just thought, it's a sponge, it's water. That very simple process of building soil through composition, piles of dead wood, actually is another way to catch and hold that moisture in the landscape. And again, it's just high up in the hills in Wales. This is a very, very valuable thing. We need great quantities of this kind of stuff going on. Think about it, is all of the activities that we're kind of promoting and interesting in permaculture are all about slowing down that pathway of water, making more complex journeys for it, more interactions, and it being held as a reservoir in the bodies of many, many different kinds of species that are all working together to maintain fertility. So I like this picture. I'm going to stop. I've got a couple of little videos and a few closing thoughts. We're okay for time, but we've got loads of time. Perfect. Okay. Let's explore this picture. And it's I'm not sure what its title is. Trees in a whole system. So we've thought about, we're kind of moving into thinking about forests. So I'm going to enlarge on sort of forest gardens and tree systems next. And we move from soil to water, and then the relationship between soil and water and the plants on it. I like this picture quite a lot. So let's look at this element here in the middle. We have a tree. So we could think of it, the tree could be a single element, or we could realize that the tree is actually quite complex in itself, and then maybe the tree itself could be a community or a cooperative. It's a guild of actually many different species living together. He's saying maybe we could think of each branch of the tree as an individual, or each root as an individual. It's responding to its environment. It's having a unique experience. It's being eaten. It's growing. It's, you know, it's dynamic. Anyway, so within our community, we've got our tree. The tree has lots of edge, it has lots of nooks and crannies, it has holes, it has bark, it has texture, it has leaves, it has seeds, it has, you know, crevices that maybe birds can nest in. I think I see a little squirrel there. Things can live on it, in it, within it, you know, around it. Look at it, lots of insects. So it's thinking about that. As a tree is growing, it is also being constantly eaten. So here's a little bug of some kind eating the leaf of the tree. Calls it a manufacturer. It's as it processes that organic matter, as it processes the tree, this insect now is returning its droppings to the ground. You've all seen that honeydew. Sometimes you get just coming out of the trees. That's insects eating it so fast, and it's almost like sugar's just dripping to the ground, and that's then being incorporated into the soil and feeding the bacteria, feeding the soil microbes. So this tree might be losing energy here because it's being eaten, but the energy is only going so far as to be returned back through the root systems and back through the microbes. These populations of leaf-eating insects are being regulated by the birds. And again, the droppings of the birds are returning those nutrients back to the surface of the soil. Maybe the tree is mining nutrients, or nutrients are traveling from deep down, right the way up into the cavity of the tree, where they're being processed and being returned to the surface of the soil, where they can then become made access to by other plants and other organisms. See how the surface of the forest soil is beautifully protected by these herbaceous layers as well. So we haven't got any bare soil, surplus nutrients, different little habitat opportunities are being created. We've got burrowing animals here as too, all part of regulating the system, all part of keeping it in some kind of a balance, all part of this, this constant movement and translation of materials between the soil, between to the canopy and back down again. And they're being translated and processed and put together and broken back down again by all these different components in the system. Let's think about how this community, this cooperative, this tree cooperative, interacts with this one. Bill's encouraging us to look at this as a guild. He's trying to think about how each one of these elements is all part of the same system that creates a tree, creates a forest. And we're being reminded here that the mycorrhiza, the fungi that work with roots, actually can join the roots of one tree to another one. So literally this tree can send sugars, nutrients, enzymes, hormones, water. It can channel it through its roots into the mycorrhizal fungal net, and then that can then channel it into another tree. Trees can communicate with each other through the mycorrhizal fungi. The wood wide web, as David Jack, the forest garden author, called it. They know this to be true. You can dig it up and you can kind of see it, but there was some German foresters were looking at an ancient tree that had been cut down in a mature forest where there's very little light reaching the forest floor, and there's the root, the trunk, the root that of the tree that's been harvested. And they looked at it, and it's still alive, and it's still growing, but it's been cut down by over 100 years. How could that be? It's not receiving any light. It's not photosynthesizing. So how could it still be alive? And the realization is the trees around it were still channeling enough energy and nutrients to that tree stump for it to carry on growing. It's fascinating, isn't it? So we can start to think of these these guilds or as families, that these are actually, they are cooperating on a meta level too. This, to think of this tree as a cooperative is one thing, but perhaps to realize that the whole forest in some way is connected, and there are messages passing between them, whether they're hormonal messages through the Wood Wide Web, or they're things to do with pollen and fertility. And we think about there's molecules being exchanged between all these elements continuously. Animals are interactors and messengers and distributors of nutrients. Actually, also fungi are very good distributors of nutrients. Fungi will grow in intensity where there's a lot of nutrient, and then they'll send fungal hi-fi out in all different distances, which in essence starts to spread out those nutrients. They can channel it around. So maybe we don't need to do so much spreading of compost and spreading of organic matter through systems. If we just, as long as it's there and put it in a big pile even, it will break down, and the mycelium will wick it away and spread it away. So there's something to think about. Very interesting. So materials enter a system and are changed and converted by the system. Think of a guild as a community of plants and animals, and the tree controls the health and the breeding of the browsers. So if the tree is abundant, the browsing, grazing animals and insects are also abundant, and then that also then feeds into this wider cycle. So it's really interesting to think that. So, and obviously all of these interactions represent a flow of nutrients and a flow of moisture that's constantly held within the system, but it's moving around. It's not staying still. And another element that Bill's added into this diagram, which I think is important and nice, is he's put a nice little seat there at some natural boulders, and there's a student of permaculture observing and interacting, and we're invited to see the system is acting as a teacher. If you watched In Grave Danger of Falling Food, Bill says quite boldly early on, he said, if we lost all of our universities, we will have lost nothing. If we lose our forests, we've lost everything. And I think to a certain extent what he's saying by that, he likes to say provocative things. He likes to get people thinking. But what he's sort of saying is, if we lost all of our learned information, we lost all our books and universities, we could relearn it. We could figure it out again. It's not impossible. But if we lost the forests, we've lost the thing that teaches us. And therefore, we can't get that back. So once we've lost certain things from the system, they're gone forever. But if we haven't lost the system, we can always go back and relearn. So here is somebody relearning, being educated by nature. So as much as I'm giving you all these ideas in this sort of slightly disconnected way through the internet, is I want you to go outside and poke your finger in the ground, to taste things and test things and allow nature to be your teacher. Allow nature to be your teacher. Yeah, okay. So there we go. Yeah, I'm going to stop there just for now. There's so much detail to go into. I am very interested in biochar. Well, we've got a little animation of mycorrhizal fungi. I don't think I bookmarked this. I think it's a little short thing. Let's have a little look at this. It's only a minute. This is just expanding a bit on the mycorrhizae fungi. So mycorrhiza is the term used to describe the symbiotic relationship between mycorrhizal fungi and the plant's root system. Am I on the right?
80% of plants live in a symbiotic.
lost my thing. Sorry, 1 second. Share screen, video, share, go.
Relationship with a remarkable organism called mycorrhizal fungi. Through this symbiosis, the fungi and the plant naturally develop a lifelong bond of mutual benefit that's existed for over 450 million years. Mycorrhiza is the term used to describe the symbiotic relationship between mycorrhizal fungi and a plant's root system. First, the spore of mycorrhizal fungi germinate in the soil and make their way to the nearest roots. The roots are then colonized by the fungi, and mycorrhiza are established. The fungi penetrate the root and create an internal network of fungal structures inside the root cells, where the plant and mycorrhizae exchange sugars and nutrients. Finally, the hyphae continue to develop outside the roots, forming an extended network of fine filaments, which cover up to 700 times more soil area than the plant's own roots. This secondary root system draws in extra beneficial nutrients and water, supporting a plant or tree for its entire lifetime.
Degrees Fahrenheit on the skin of this kiln. Not simple.
It really doesn't.
Okay, that was a quick, short video of mycorrhizal fungi. And then it jumped to the next thing, which was just in the playlist, which was about making biochar. And I wanted to mention biochar in the soil water thing. So this will be our kind of it's only a 2-minute video. So we've got a couple of minutes to think a bit more about this. Now I'm going to explain how we make biochar, what it is in more detail in a separate presentation. But I want to wet your whistle, as it were, to get you excited about it. Share screen, this one, share, okay. So I really like this experiment. This is a fun experiment. I've done it myself. But firstly, let me show you this. This is a piece of wood that has been pyrolized. If you can see the pores, you can see its structure, can't you? If you listen to that, if you hear that, it's totally hollow. There's nothing, it's full of air. If I pull it apart, can you hear that? Tinkles like glass. Yeah, it's because it's hollow. So this is a piece of wood that's been cooked. It's been put in a kiln where it's become very, very hot. And what happens when you do that is, firstly, all the moisture in the wood evaporates. Obviously, goes off as steam, and then anything that's left in the wood that is not carbon is driven off as a gas. That gas is highly flammable. It contains methane and hydrogen and also volatile oils like creosote. Most things you can burn and you can use those for other things. So when you've driven off, and some people say, you like to ask me, what's the difference between biochar and charcoal? And the answer is, well, they're very similar. Perhaps the difference about biochar is how you intend to use it eventually. But there's another difference, which is that this has been made precisely. This has been made quite scientifically. You can make charcoal just in a mound in the ground, and what comes out, the charcoal that you cook on, is oily. You have not got rid of those volatile oils. It's still, so it's potentially toxic, but also it's more flammable. It's easier to light because it's still got those volatile oils still within it. So if you handle the charcoal you buy in a garage or whatever you buy for barbecues, if you handle that, it makes your fingers very black and dirty. Whereas if you look at this, I'm handling this and it's not making my hands black and dirty. And that's because those volatile oils have all been driven off and combusted. And we'll talk about that later, what wood gas is and what we can do with it. What's so interesting is this residue, this hollow residue. So it has an enormous surface area inside it. Because essentially plants are lots of tubes, aren't they? Think of those tubes, think how water wicks up from the roots of a plant right to the tips of the leaves on the top of the tree. That there's little pathways, there's roots through, there's tunnels, there's tubes. And so when we've dried this out, we've cooked it, we've driven off everything that isn't just the structure, the basic structure of the plant, the carbon. What we're left now, this is 100% pure carbon. It's got nothing else in it. There's no water, there's no oils, there's no other plant residues. This is the basic structure of what plants are made of. So if I crush this up, it's still maintaining this complex. I've got some microscopic photos of charcoal. I'll show you later. But if I was to crush this up, it's still full of a matrix full of tiny little holes, you know, think like a sponge or something. The surface area, a teaspoon of biochar crushed up could have an acre of surface area. So when we've got lots and lots of surface area, if we bring that into contact with water, the water can cling to those surfaces. So it turns out that if we crush this stuff up and add it into soil, the ability of soil to hold water greatly increases. The ability of soil for that water to percolate into the soil greatly increases. The amount of air in the soil greatly increases because we're essentially folding in air spaces. So amazingly, heroically, incredibly interestingly, is we can work with biochar, adding it to soils in a way in which it makes the soil much more fertile. And that's intriguing and difficult to understand in some ways because this is not plant nutrient, it's only structure. And this is an inert thing. So in other words, if I put this into the soil, it will just still be there, maybe in 1,000 years' time. So how can something that's inert create fertility in a soil? And the answer is edges. We're folding in edges, surface area, air pockets. Think of those micro pores, those little cavities that I was celebrating in an earlier diagram. Is hello, we can multiply that effect enormously by strategic placement of elements. We can introduce this into a system in a way in which transforms the system. So I've got this on the video picture and I'm talking to you. Let's watch the video. Here's a fun video playing with biochar. You might notice a cup of water on one side and a cup of biochar on the other. Let's, how do we play the video? Here we go.
All right, we're going to test that the water retainage on our biochar holds and doesn't take any more surface area than what the water would be. And we are same level full on each container. So now the full glass is in the full, or the 3/4 full glass of water is now in the 3/4 full glass of biochar, and it did not overflow, and it will be the same level as what this water was, showing that the water capacity retention absorbs into the biochar. It didn't fill up very much more. It's pretty much leveled out. So it filled the glass up maybe a half inch more than what it was. But that shows how much water that biochar can hold and retain.
Okay, we'll break out of that. So what he's basically demonstrated to you just then is that this is more air. Sorry, YouTube autoplay. What's the next thing? What he's just demonstrated for you really is that this thing is much more air than it is matter. So although it looks solid, it's mainly air. So introducing this into soil means we're folding in lots of air. We're creating, greatly increasing the ability of the soil to hold water. And by bringing in air, we're opening up the possibility for much more fertility because we're going to have more microbial activity. Think of that compressed soil against the uncompressed soil. These are the kinds of insights that I'm trying to build up in you through these lectures, is to get to this point of just how important surface area is, just how important air and water are, and just how biological the fertility in soil is. Now, when we start bringing these things together, we can create massive transformations. So as much as I keep pointing to the very, very real problems and challenges that we have in terms of climate change, soil erosion, habitat loss, et cetera, there are very, very powerful things that we can do that address that and change it. Now, as I already think I've said, this is basically inert. If I crush this up and put it into soil, it will still be there in 1,000 years' time. So what I'm saying to you also is long-term stable forms of soil carbon storage in soil is a big part of how we solve our problem. So, and how we helping people meet their needs with natural and local resources. How important is this stuff? So one of the things that we're going to do at the weekend at Trevlack Farmers, I want to make some biochar. And I want to have some fun playing with these elements and starting to see the possibilities. And then in week 2, we could also think a bit more about how we can use these things as how we can use them usefully. Now, there's so much that isn't known about this. This is kind of a new thing, and it's a new old thing. And again, with time, I'll explain more. But it turns out that traditional farmers in the Amazon, up until about 500 or 600 years ago, had been doing it for 1,000 or 2,000 years. They'd been using this as a farming technique, and actually they managed to build some of the most stable and fertile soils in the world are in the Amazon. In those tropical soils that I showed you in the diagram earlier, I said aren't very good for farming because they're so fragile. Well, there were people historically who learned how to farm them. And I think that what we can learn from them is enormously exciting and interesting. So permaculture is ready to learn from all sources, from ancient, traditional knowledge, and also from modern scientific knowledge. And always asking, how can we bring these things together to help meet our needs, meet community needs, whilst respecting and honouring and working within the carrying capacity of our own ecosystem, of the planetary ecosystem. So our Earth care, people care, fair shares. Okay, we've just got a few minutes left. I'm very happy to have questions or feedback. Let's have a quick little go round. Any points anyone would like to just give a comeback or any thoughts? Happy to hear that.
One thing I heard was that biochar can hold nutrients as well to stop them washing away. So not just water and air, but nutrients as well, and store it, for the plants to get.
When you realise that the nutrients are the microbes, the nutrients are the bacteria. They're going to move. This is a skyscraper. This is an apartment block for millions and millions of microbes to move into it. So yeah, it's like it's like a coral reef within the soil that allows a purchase and place of things to settle and to be.
One video. Sorry, my partner didn't realise we were on video, just walked past.
That's okay. He seems decent. He seems dressed.
Yeah, that's really funny. I've lost my train of thought now.
I think we all have.
Sorry.
That's quite okay. Don't worry. But yeah, any thoughts about soil and water and all this sort of stuff, and how, you know, these really big picture ideas, we're relating them to a very small picture, you know, your garden, your allotments, whatever. But it's all very important to think about how it all fits together at a bigger scale. Yeah.
Well, yeah, I think like the biochar, again, talking about my pots, keep going on about them. So that would be something that would be great for maintaining storage of water in a smaller vessel, really, wouldn't it?
Absolutely, yeah.
Yeah.
Really important. And we'll think about how to make it, and also how there's different ways we can inoculate it and populate it with beneficial microbes, the things that your plants are going to like to build relationships with.
Mm-hmm.
Great.
Yeah, great. Just can I mention about tomorrow as well, because I'm going to be getting the train up.
Okay.
So I guess the day will work the same, like 9 till 1.
Yes.
Lectures, and then I'll probably leave after lunch, so get the train up, which means I won't be available for the evening lecture.
Yeah.
But I guess I can just access that at a later time anyway, can't I? Because it'll be on the blog.
Yes. And I'll think about that. So tomorrow is Thursday, isn't it?
Mm-hmm.
So Thursday I go and visit my aging parents, and so I can do it from there. I can do it from their house. So I'll go over there tomorrow afternoon, and I'll do a little evening broadcast to set up the weekend, and then I'll come and, well, yeah, go on. You say what I haven't quite thought this all through. It's going to be helpful. You're going to be at Trevlack on Friday.
Yeah, I'm going to go up tomorrow, so I'll stay there the evening before, because I think we start at 10 o'clock on the Friday, don't we?
Yes, that's it, yes.
So I think it just makes more sense. I think you encouraged me to go up Thursday, so
Great.
I'll be there ready, depending on signal, as whether I can see the evening lecture or not, so that's fine. And then...
They have good internet on the farm, but not out in the field, so...
Okay.
But you can come and there'll be I'm sure they'll be able to sort you out with that.
Okay, cool. I'll give Ian a ring, I think, and just let him know what time I'll be there. And okay, cool. I'm actually gonna stay in one of the yurts. Thought I'd treat myself.
Lovely.
So I don't have to carry the tent on a train then as well. So
it's a really, really good plan. Great.
That's what I thought.
The weather looks good as well, so hopefully we're going to have a fun weekend.
Okay.
We are going to be, I think, 6 people, so we're also technically obeying the law of the land, which is also a great thing. So sadly, Lydia, although she's normally free at weekends, she's not available this weekend.
Oh, that's a shame.
I've invited, or just another separate line of it, is my cousin, my Alison, and her partner Vincent are going to come over they live in East Anglia. They're going to come and join us for the weekend, but they won't come till Friday night. And they're novices to permaculture, but they really they're so keen to have a bit of a conversation to get a feel for it. So I just said, look, come and join us on the farm. They're lovely people. She's a nurse. He's an artist. You'll enjoy meeting them. And great. So
fabulous.
We shall have fun. What are your Sean is coming in a caravan, I believe. What are your movements, Sean?
Well, I was going to watch the video at 1 o'clock and then drive up. I'm near Red Hill in Surrey, but I think it's only 3.5 hours. So
okay,
I should be there late afternoon and watch the evening video. You know, to get
lovely. And the farm's great. And to say, I've been teaching permaculture there for 10 years. Not continuously, but we did our first courses there 10 years ago. And then more recently, we've gone back. And he's taken it all on board. He really has. And we've seen a transformation over a decade. So there's a lot of things to reflect on there and to see. And I hope to really, in the process of being able to really bring a lot of this to life. It's all been very theoretical so far. So I want to kind of bring us more into slightly more practical and, to really actually see things. And there's loads of very interesting processes going on the farm. So
what was it you planned? Was it 4 days on the farm as part of this course, is it?
Yes.
The outline? I haven't seen any outline
Right. Okay. Yeah. I kind of imagined it as 3 blocks of 4 days. So we're going to do these 4 days, 4 days on the farm, and then we'll do we have to do a design activity. So then we'll do a kind of a design workshop, and maybe when we're together, we'll just finalize the times for that. So make sure that all suits. But basically, I think I imagined having the Monday off so that we could all, put everything back together again, and then Tuesday, Wednesday, Thursday, Friday. I think is what.
Okay.
Yeah.
Yeah, I think I'll travel back on the Monday as well.
Yeah. Okay. Yes.
Yeah.
Okay.
Perfect.
So we'll make the most of that Monday, but I understand that people need to travel. Yeah. And
I haven't paid you as well.
Oh, that would be nice.
How do I pay you?
Well, actually, we could do. Oh, where is it? I was going to get. I can put my bank thing somewhere. I can tell you my numbers. The Sector 39 account. Sorry, Michelle, we're going to talk to you in a second.
Yeah, no problem.
I'm going to put my account number in the chat. So the sort code is 0899. No, 9299.
089299.
That's the sort code. Whoops. Why doesn't that? Oh, it's because I'm sending it to Lydia. Hang on a second, everyone. There it is. 089299, and the account number is 69721948.
Steve, can I just pay you cash at the weekend?
You may. Thank you. And also, they sell food at the farm. They have a shop. They have fantastic. If you're a meat person, they do have really nice free-range, organic, grass-fed, pasture-finished animals in pieces, and also a whole bunch of other stuff as well. And they make pies. He makes his own pies. So if you're a pie person, you're going to have a lot of fun. And yeah. Anyway, so yeah. How about you? What are your plans, Michelle?
Yeah, I guess I'm going to come up on the Friday morning.
Okay.
And yeah.
You're there for 10?
Yeah, for 10, yeah.
Only an hour from Newtown to Trevlack. If you come straight up the main road towards Oswestry.
I was there a few weeks ago at the One Planet Development course.
Oh, of course you were. Of course you are. I'm being stupid. Yeah, of course. Yeah. Okay. And if you put it into Google Maps, it comes up. It's not hard to find. This is a little bit, a little bit of a back road, but it's any problems, let me know. Yeah, anyway, so I'll see everyone this evening.
Steve, are they doing food over the weekend again then?
Yes, I haven't actually just checked he's on holiday, but he's told me the other day they're very happy to supply food because it's all their own produce. So he doesn't have to sell it for a lot, but it's all not profit. You know what I mean? It's all income for him because it's all self-generated. They grow the feed for the animals on the farm. They produce the animal, they get them butchered very locally, and then he says direct sales of the meat and any extras goes into the pies, and they grow the veg for that. They do vegan and vegetarian and gluten-free stuff as well.
Do we have to order food then, so that they know how many of us come in and what we want?
They can cope with that. I'll give them a sense of that. They'll know the size of the group, and I'll give them a sense of that. Bring a few things for yourself as well, if there's things that you particularly like, a particular breakfast cereal or something. But otherwise, there's a little shed, a building we can use for teas and coffees and eating under cover. I think the weather's going to be nice, but even if it isn't, we will have fun either way.
Is it worth bringing wellies?
Yes.
Absolutely. Yes. Yeah, bring all weather gear. If we get a bit of weather, then we don't want that to spoil our fun, do we? So
no.
It's great, and I'll structure some activities, but we'll have a chance to do a bit of walking and talking and reflecting really on all this sort of information I've been sort of throwing at you. So I hope it turns to. I try to cover as lot of ground as I can on the first few days of the PDC, and then we start to kind of work with that information and think what we can do with it. I'll bring the books, and I've got loads of videos and things like that. So if you bring a memory stick or your own laptop or something, we can do some file transfers as well if you'd like. I do have a ton of resources, and I'll bring a a big box of books that you can look through as well. Many of which I also have on PDF, so we can do some copyright infringements as well if you like. I just think this
we're gonna plan to have a campfire, Steve.
Oh yes, we should have as much. Yeah, I mean, I think sitting around campfires and maybe imbibing a beer or two as well might be part of the agenda. So.
Oh well, if we have to.
Well, usually if I'm involved, yeah. Okay. Okay.
My caravan, so if you want to cook on that.
Yeah.
All right. Okay. Nice one. Sure. So you'll be fully kitted out. So. Great. Okay. So we'll catch up again. Today's Wednesday, isn't it? Yeah, 7 o'clock, and
Okay.
we'll go a bit further into biochar and a bit more further into catching and storing energy. And so the next principle is obtain a yield. Obviously, we're doing all of this catching and storing energy so we can feed ourselves, so that we can create income, so that we can meet our needs. So that's going to be the next thing. So, and principle 4 is about systems and about how everything kind of is connected. So as we come to the farm, we're thinking about yields and systems, and natural resources and local resources. Those are the sort of the themes. It all fits together very, very well. And hopefully things will start, usually by day 4 or 5, things start to join together in your mind. You start getting kind of, big aha moments, kind of quantum leaps, hopefully. That's what we're trying to get to anyway. So great. I look forward to seeing you at 7.
Fab.
See you later.
Okay, bye for now.
Bye.
Bye-bye. Bye, Sean.